Hey everyone, it's me, Steve. Today I will be critiquing Eric Hovind's latest miserable attempt to try to convince you that a literal interpretation of the Great Flood in Genesis is somehow scientific. Well, spoilers, it's not. Now, I originally made the video you're about to see. It was originally a lot longer. I went through his entire video originally, and I would stop it and interject points with actual references, which you're going to see throughout this video, but I will not be showing any actual video from his video. I do not want a copyright claim or strike, okay? You will hear some audio leading up to it, but I'm not going to run you through the whole thing because my original video is like 5 hours long. I'm not even kidding. It was made for somebody else who is going to pick what they need from it. And you'll probably hear a lot of the same things on their channel as well. But I just wanted to give you the breakdown from a geologist's perspective on how this whole thing is just another miserable attempt to fit a square peg into a round hole. Anyway, that's it. Let's get started. And welcome to another increment of Eric Hovind's BS seminar. All right, this one was alerted to me by Paul, and I'm going to go through this whole thing from a geologic standpoint. I know, those of us who know that the flood is not a literal event know that everything from physics to chemistry to biology to archaeology to history shows that it never happened. I'm going to have to do this in a very lengthy way because unlike how young earth creationists present things, I want you to be as informed as you can. I know you guys are not professional geologists. I get this. But you need to have understanding of things in order for me to talk about things and show you their BS. See, what Hovind and all the other young earth creationists are hoping when it comes to geology is that you are uninformed, that you think geology is just rock identification and going, ooh, ah, isn't that cool? And then everything else is interpretation. That's not what we do. There are so many disciplines, subdisciplines of geology that aren't even addressed, that most of the public isn't even aware about. And one of those ones, which we're going to go into a little bit here, don't worry, I'll keep the maths out of it. There's a lot of maths in this, is structural geology. It's a lot more like engineering than geology. We use a lot of the same tools that engineers use. We use lower southern hemisphere or southern hemisphere stereo nets. We use more circles. We use all these tools that engineers will often use, except we apply it where we can to the natural world. Now, unlike engineers, us geologists understand the natural world isn't in black and white and varies, but we can still use some of those tools. They do work in making predictions. And structural geology was the first subdiscipline of geology that actually made any real predictions. And where they're going to take you is where this was born. I don't know why the word dells is in the title of this Young Earth Creationist video by Eric. They spend maybe, I don't know, a few minutes at the dells, and the rest is in an area called the Baraboo Hills, and us geologists know as the Baraboo syncline. Now I'm going to have to give you some background, but I'll do it as appropriate. I'm not going to get into it right away because I'll do it as we go. Let's get a little bit into this here. Let's start playing.
Partners of creation today.
God apparently couldn't pass a grade school science
I'll address this, but first I want you to watch it.
class.
There's no scientific evidence to support a global flood.
Evolution has resulted in the countless species that have lived on Earth.
Great landmarks are the work of millions of years of slow, imperceptible erosion.
Either way, you don't need God, so here we are in our bubble of just us, trying to figure out what's right and wrong.
They're all denying the worldwide flood.
Okay, this is a common tactic of young earth creationists, and those of you that have been in that camp are aware of this. They try to equate science and geology quite often. I'm not going to say secular geology. There is no secular geology. There's geology and the crap they're trying to sell you. Science is science. There's no secular science either. But did you see what he did there? He showed you videos by people who there's no need for God or whatever, or, the God of the Bible, couldn't pass a science or whatever. Science does not deal with whether or not there is a creator. If there is a creator outside of space-time, we cannot test that. It's a non-issue. Now, are there people who sit there and say, yeah, you don't need a God to get the natural world to work? All right? It's not necessary, but that doesn't mean there isn't one. And this is something that young Earth creationists do. They try to equate science, and especially evolution, with atheism. They try to make these synonyms, and they are not synonyms. There are very many very religious people who have no problem accepting science. All right? It's just this little circle of these people here, young Earth creationists, that in order to sit there and sell you what they're selling you, they got to play the martyr card of the victim a little bit, because that is an appeal to emotion. People can recognize that. Oh, I've been the underdog. Oh, I know I've been right and everyone else thought I was wrong, so maybe I can relate to this. It's a psychological tactic is what it is. It's not evidence of a flood in any way, shape, or form. All right, let's go on a little bit here.
They have no idea they are fulfilling prophecy as we.
Okay, I'm going to skip this part a little bit. It's just him ranting about prophecy and the next guy getting his team together. I'm going to try to stick with the science here as best I can. These, the philosophical part of it's talk for another time. I just want to say real quick before this gets into this, I'm not going to question the qualifications or, what any of these people are. I'm just going to accept they are who they say they are. But I will address one guy in particular when we get to him.
To Operation Wisconsin Dells, we've gathered you here for a very specific reason. I want to introduce you to some of your team leaders. We've got Jay Siegert, PowerPoint and presentation extraordinaire.
Okay, I have never brought a PowerPoint guy with me on a geologic, field trip.
We want you guys to be able to give powerful presentations about what you learn. We got Tim and Tim. Little Tim, Big Tim. We'll go with Tiny Tim, just for sake of not getting them confused, all right? Tim is a local geologist, going to really help you understand the geology that you're seeing. Big Tim is going to help us out with theology, making sure that what you learn. We've got Dennis Seiler, team captain.
I don't even know why this guy is there, but actually I do. But let's get through.
The one who's heading up this operation, making sure that we take this not only for ourselves, but send it out to the world. And then we've got Mr. Rockman himself, Dr. Steve Austin.
Okay, just real quick about Steve Austin here. He is a PhD. I forget what his specialty within geology is. He is one of the young Earth creationist trifecta. There's 3 of them that are degreed geologists. We'll just go with that. He's one. Baumgartner's another one, and Snelling is another one. And they use these guys to, kind of give them some sort of authority in what they're saying. Oh yeah, somebody else, somebody with an actual secular degree. Notice sarcasm in my voice there. Now, if I was to put a team of people together to lead a bunch of students or lay people into the field about geology, I'm going to have either myself, who's a licensed professional geologist, and you will not see professional geologists in young Earth creationist ranks. Why? Because in order to be a professional geologist, like a professional engineer, or to be a professional lawyer, or I forget the name of their certification, whatever it is, it's a recognized profession. So you can get a license in it, like you can recognize professions. So if you do that, and then you go about giving information or that isn't correct, that is false, that becomes an ethical issue. All right? You're not going to lose your degree by hooking up with young Earth creationists and following them around and repeating their dribble. However, you can lose your license doing something like that, right? Or at least put it at risk. Now, the thing with professional licenses is, you can believe whatever you want. I don't care. My concern is misinformation. And that's what they're doing here, all right? And you can't hide behind religious faith to the nth degree. At some point, you're going to be accountable for what you're doing. Now, I understand people make mistakes and errors. I'm not talking about that. I'm talking willful, false narratives, misinformation given intentionally. There's got to be that intent there. So I would put together a geologist, maybe two. I might bring somebody with me, like if there's a speaker you want to use, someone who's good at speaking, I get that. Like with time teams, they have Tony. Tony is not an archaeologist, but everyone else around him is, or they're an expert in the field that they're working at. They may not be an archaeologist, but they may be an expert in like Neolithic tools or something like that. That's appropriate, all right? And that's fine. What isn't appropriate is this. You have what? 2 geologists and 4 people who know what about geology? I mean, it's not the kind of team you put together, and I probably wouldn't have so much of a problem with it, but these lay people, and that's what they are. Okay, the PowerPoint guy, the ministry guy, Big Tim, they are lay people. They start giving lectures. These are not the people you have when you're actually trying to learn geology in the field. All right, this isn't the kind of crew you put together. It's just not right, in my opinion.
Thank you guys for joining us. They're going to be taking us, showing us things that you need to take out to the world. You guys are all familiar with the prophecy. In the last days, people are going to willingly ignorant of a couple things. What are they? Creation. What else? The flood. What else? The coming judgment of God.
Prophecy requires zero evidence, and it's only filled in hindsight. All right? It's never predicted anything. This is the only part of the devils they take you to.
This used to be 60 acres of pristine lake with a beachfront.
However, the natural world doesn't care. Whenever we as humans build something against nature, in this case an earthen dam, if we don't maintain it or don't build it to withstand certain things, it's going to fail. Ultimately, nature wins, humans lose. All right? It's unavoidable. Okay? So trying to equate something, and it's not really an analogy. Young Earth creationists don't really do the analogy thing. They do the false equivalence thing. Analogies in science, you'll never see them in papers, but they're limited in scope and they're teaching tools. All right, it's to get you to understand kind of something small. Like my textbook, you'll see them in textbooks. My structural geology textbook has an analogy in the first chapter, but it's limited in scope and it's to sit there and give you that tiny eureka moment, and it's intentionally not an equivalence, all right? But this is trying to equivocate something and then extrapolate it to the nth degree, far going beyond the scope of any analogy.
Now it's a mere 20 acres of water that nobody wants to go in. Why?
Okay, he gives a decent explanation here. There's a word he uses that annoys me. I'll come back to that.
Catastrophic dam failure. Check it out.
I want you to look at this. Yes, this dam failed, okay? And you can see where it is. Follow my cursor if you can. You see, here's the dam. Look at this right here in the center. This is a scour pit. Just go with that. And this is where the water catastrophically outflowed, all right? I don't know how many of you have ever taken a hose as a kid and you had a sand pit and you stood there and you let the hose, it forms a little scour part in the middle, right? That's a lot of water really fast and the sand gets easily eroded. That's what kind of happened here. See, that's an analogy, all right? It's not an equivalence, limited in scope. But you see here, it just took everything with it and pushed it downstream. It just scoured the landscape. Now, this is a very local event, and he's going to draw on that to make some false equivalences later. This is just a tiny local flood due to a dam failure. All right? Do we get natural floods and debris flows? Yes, we do. But not like this. This wouldn't have happened if we hadn't put a dam here. And you can see the kind of landforms, geomorphology that forms even during a small flood event. You get the scour pit, you get everything stripped downstream, okay? This isn't what we observe in the geologic record, but let's just...
Look at that. Thousands of cubic yards of sediment removed in just a couple hours. See, when a dam breaks catastrophically, it makes a catastrophic cycle.
Okay, this is the word I have a problem with. I'm going to skip the rest of his little talk about because it's actually an okay description. We don't talk really about a dam failure in cycles.
It erodes a little bit from the top, and that gives a whole lot more water because of the new elevation of the stopping point. A whole lot more water is now capable of going over that dam. Way, lowering the level that is stopping the water. So that cyclical catastrophic cycle is what allowed this entire.
See, the water came over, ripped the dam away, and you get the scour pit in the middle. You get a better view of it here. This cliff here is Cambrian sandstone. The bedrock here is Cambrian sandstone. He's going to actually bring
the lake to drain, eroding directly into the sandstone. This is Cambrian rock. Notice how it's all stratified. It's laid out in layers, and you can literally pick the layers up off the other layers. This is an indication that all of this sediment was formed in moving water.
Yeah, but we know moving water can create a lot of different sediments. We have moving water all over the planet today. We don't need a catastrophic flood to move sediments around. Anyone who's watched a pebble roll at the bottom of a river knows this. Anyone who's watched the sand come in and out on a beach knows this. This isn't rocket science. This is simple, basic observation. You don't need a catastrophe to move sediment.
It's called sedimentary. 700 feet below us is where we get the great unconformity, where the bedrock meets the Cambrian rock.
Okay, he misspoke there a little bit. Yeah, not about the great unconformity, which I'll address here in a second, but what he has in his hand is the bedrock. He meant to say basement rock when he's talking about 700 feet down, which is where the Precambrian is, but the Precambrian outcrops at Baraboo. You're going to go to that. It outcrops at places like Baxter Hollow in the area. It outcrops in many other places in the area they don't take you to. All right? And there's reasons for that because it doesn't fit the narrative. And even where they take you doesn't really fit the narrative. I'm going to have to give you a background on the Baraboo syncline before they get into it because I want you to be informed. All right? But first I need to say something about the great unconformity. And we're just going to get into this here. They love their Grand Canyon. But, let's see. I am going to show you something actually from Arizona State. Let's do this. This is, all right, you see this here? This is from there. I believe, let me get you the site, because I want to get you the citation. Grand Canyon, is this it? Okay, that's a time scale. We'll come back to that in a second, because I do want to do that. Okay, here we go. This is actually the information you need. All right, this is where it came from. There, that's called citing things. Learn to do it, Eric. Okay, so here you look here, and this is just a very simplified. You're going to see me do this for Baraboo area too. All right, this is just a very generalized cross section, if you will. A cross section is a slice into the earth. A geologic map is a plan view, and you're going to see that. This is a cross section, and every geologist who makes a geologic map does a cross section. It's a way to check ourselves because contacts aren't exposed everywhere. Okay, it's a way to check ourselves to see if what we did, our interpretations, because you do have to do some interpreting in the field. You do make measurements, which we'll come back to, but to see if it works, to see if it's logical and makes sense, okay? And this is that. Now, the Grand Canyon has excellent exposure, all right? So this is just a compilation. And what you see here, and this is typical, I'm going to bash the Phanerozoic guys here for a second, just so you know, the Phanerozoic, let's get the geo time scale here. Okay, this is the working GSA time scale in North America. This is what we use. There's an international one that's almost this verbatim. It's a little different. But when you look here, what I want you to get out of this is you look here, you see the Cenozoic. And we go to the bottom. That's from 66 million years ago to today. All right? You get to the Mesozoic. That's from 251.9 million years ago to 66 million years ago. You look at the Paleozoic, 541 to 251.9. The Cenozoic, Mesozoic, and Paleozoic. So from the beginning of the Cambrian, which he's going to talk about here, 541 million years ago, to today is the Phanerozoic eon. All right? From 541 million years ago to today. And it's all these divisions. And if you look at this time chart, you'll see it's Phanerozoic biased. Why? Because the more recent we get in the geologic record, the more geology we have preserved. It goes that way for anything. You know, you have more available. You have more to study. As you go back further in the past, the record gets eliminated. The Earth is really good at getting rid of geologic evidence. But there are still some places really observed. And if you look here, this is the Precambrian. So it ends at 541 million years ago. But it begins at the beginning of the Earth. So about 4,500 million years ago, 4.5 billion years ago, is when the Precambrian begins. That's 88% of Earth's history, all right? But the Precambrian is not an eon. It's actually not even a formal geologic unit. It's a waste bin. It's a waste bin term that we still use because it's a holdover. Because in the early to mid 19th century and even to the late 19th century, we were still trying to figure this stuff out. We were still trying to figure stratigraphy out. And we weren't sure if the Precambrian was as long as the Phanerozoic or shorter, same time, longer. We didn't know. There was many people thought it was about the same time. So if we assumed the Phanerozoic in 1850 was 500 million years long, which we didn't, but just for argument's sake, we would probably assume the Precambrian was 500 million years long. But boy, were we wrong. We didn't start realizing this until radiometric dating at the turn of the 20th century. And we started to know the Earth was really old, but we didn't have an actual age until mid-20th century. Talk for another time. But I want you to look here. So see your eon here for the Proterozoic. 2,500 million years ago to 541 million years ago. That's almost 2 billion years for an eon. Okay? As where the Phanerozoic eon is only 541 million years. You getting the idea here? Us Precambrian guys hate this time scale because it's so Phanerozoic biased. And you're going to hear me, just so you look at it, you hear me use the term Paleoproterozoic, Mesoproterozoic, I may say Neoproterozoic. We're going to basically work in this area. But we will maybe talk about the Archean and stuff too. So I just wanted you to look at that. Let's go back to the Grand Canyon. Proterozoic. All right, they just divided that out. This is the bottom of the canyon. Young Earth creationists love to focus on this. See, notice this says the second great unconformity. I'm going to talk about that in a second. Here's the first. This entire supergroup here is a Grand Canyon supergroup. Now, this is not to scale, all right? They have focus on the Phanerozoic because that's where everyone mostly looks at, and that's where all the cool stuff is. There's nothing we can really relate to in the Precambrian, which the Proterozoic is the most recent era of. So a lot of people are turned off by that. It's not sexy. There's no fossils. There's no history of life. There's nothing we can really relate to. I mean, there is history of life, stromatolites, but we can't really relate to those, all right? But I want you to see here, you see the Grand Canyon supergroup is often ignored by young Earth creationists, and it's 3 times thicker than all of this in places, okay? That's common in the Proterozoic. This would have been some sort of Proterozoic basin, either a continental margin or I forget exactly what it is, or some sort of basin, intercratonic basin. And these Proterozoic basins are so much thicker than their Phanerozoic counterparts. And I'm not talking by a little bit. I'm talking 2, 3, 5 times thicker sometimes. There was something different going on in the Proterozoic that changed into the Phanerozoic. And this might have something to do with plate tectonics. We're still working this out. But like the Belt-Purcell supergroup in Montana, that's like 5 times thicker. Just so you know, he's going to use the standard system. I will try to use metric when I can if my brain can do the conversion. Okay. But the Belt-Purcell group is 5 times thicker than the entire Phanerozoic deposits in the Illinois Basin are. And the Illinois Basin is huge. So something was different during the Proterozoic. And also our mountain building events, we had a lot of accretion terrains, which we still get today. But mountain ranges didn't seem to get as high. Now that could just be some sort of preservation bias, and it's a talk for another time. But what I want you to get out of this is you see this second grade unconformity, first grade unconformity, and actually this 60-mile formation we know now is actually Cambrian. They colored it here, so this line should actually come down like this, but it doesn't. So there's two great unconformities within the Grand Canyon alone. You'll never hear young Earth creationists mention this, though. They'll only talk about the great unconformity. See, the thing with the great unconformity is it's not really a non-thing, but now we're not in the 19th century anymore. That's when this was recognized, and it was recognized here. Throughout North America, there is, in most places, not everywhere, but in most places, a distinct unconformity between the Precambrian and the Phanerozoic. This second grade unconformity was the one first recognized. Then we recognized this one. So there is no standard definition for great unconformity. Most of us, if it's less than 100 million years, we won't use the term. If it's more, it is. And Eric's going to talk about it a little bit. And it varies because conformities do not continue forever in geology, just like rock units don't. I cannot extrapolate the Tapeats, the Bright Angel, the Mauve, the Red Wall to Wisconsin, although they're going to try later. So units don't continue forever, conformities don't continue forever, and unconformities don't continue forever. I can visually show you this. Now, here, this is also on Arizona's website. And I suggest you look it up if you can. Oh, they have that down there. I guess I could have scrolled to the next page. But anyway, and this is a good general history. Now you see the actual stratigraphic units here. Now I'm going to come back to geologic mapping and lithostratigraphy later. This is not actual thickness. This is depositional chronological thickness. So we mean how long we suspect it took for these sediments to be deposited. We don't sit there and really say this formation, it took X amount of years for 1 millimeter to form, because that doesn't work. But we have good dates from the Grand Canyon, good detrital, zircon dating too, where we have a good understanding. That's how we knew the 60-mile is actually Cambrian, even though it was assumed to be Precambrian, because somebody found young detrital zircons in it, younger, making it Cambrian. And you can see these gaps. These are your big unconformities. Here's a great unconformity. All right, but look, there's a big one here. There's a big one here. This is your first great unconformity here. See, there's all these unconformities. This one's longer than this one. And you look at this line here, and you can see this is the oldest, the brown. Okay, and this is the middle, and this is the youngest. So you see here, you have more missing time between the Phanerozoic and the Precambrian, the Proterozoic here, than you do here and here. So it's not like there's one huge amount of missing time that geologists just say is, 1 billion years across a continent. This is Illinois, and this is a publication that came out, I think, the year I was born or close to it. I do have this in hard copy. This is scanned. You can find this online too at the Illinois State Geological Survey site, but there's something particular I want to show you. Showing you how conformities and unconformities don't continue forever. Kind of like with the Grand Canyon, but with Illinois. And it's temporal. Now, obviously units in the ground, strata in the ground, you're not going to see a big gap between, on the ground and 50 feet or 30 meters in the air. I mean, between it's not like the missing time's preserved in the air. The units are going to be on top of each other, but this is a temporal representation. Now, this is an older publication, but it shows you here, see these unconformities? See, even within these are all Phanerozoic. This is all Phanerozoic in the Illinois Basin. There's no Precambrian in the Illinois Basin deposits. It's all Cambrian and younger. You can see the sandstone here, and this is the Sauk sequence. This is something they love to talk about. All right? And you can see the base here is sand, but it quickly becomes carbonate. And that's a big, huge problem for young Earth creationism. Because we know through experimentation, yes, carbonate rocks can be piled up dead things, but they're not always. You can get carbonate precipitate out of seawater. And that takes, I think at best, we can get in the lab setting is 6 millimeters a year. And we're talking units that are dozens, if not hundreds of meters thick of carbonate units. That takes a little more than 4,500 years. And when I say young Earth, I'm going off Eric Hovind. He thinks the Earth 6,000 years old and the Great Flood was about 4,500 years ago, okay? So you can see that this subtype of canoe, unconformity, is generally, this is just general how it goes here. It doesn't continue across the basin. You have the subkaskaskia unconformity, also doesn't continue throughout the basin. You have conformities here. And same thing here. So you can see these unconformities don't continue forever. Neither do these conform. Here's a conformity. Here's an unconformity. Okay? So this concept of unconformities isn't the simple black and white thing Eric's trying to give you here. Okay? That's not how this works. That's not what we observe. Conformities are just missing time, and we have 3 different types of unconformities that you have to be able to physically recognize. You can get unconformities from just non-deposition. It's how bedding planes form. So bedding planes that's a disconformity. There's no erosion. There's no tectonic activity. It's just a time of non-deposition. You can get a little bit of erosion on the disconformity, but you don't need massive amounts of it. So there are even unconformities or even a bedding scale. They're not just huge regional scales. So I just want you to understand that, okay? And before I get, let's do here, Jordan Sandstone, I'm going to show you places. The great unconformity in some places is completely absent between the Proterozoic and the Phanerozoic eons, okay? The sedimentation's continuous. Let me see if I can, is this one place? No, this is a good, if you want to understand the Illinois Basin, just so you know, you heard me ramble, but this is the area of the Illinois Basin. It goes into Indiana and Kentucky as well. I'm glad I opened that so you can see that. And here's some paleo maps. As you can see, during the Cambrian, Laurentia, Proto-North America, as you can see, North America wasn't even fully assembled yet. We were missing many parts. The seas started encroaching from the east, the west, and the south, as you can see here. Okay, now, young Earth creationists try to tell you this happened instantaneously, but that doesn't work. There's some of these units do go into Wisconsin, but in order to trace a lithostratigraphic unit, which is what these are, you have to be able to continuously be very confident that it continues. Otherwise, you give it another name. You can't just extrapolate unlike units across a continent. Okay, here we go. Around the Belt Basin in Idaho. Let's look at this a little bit here. Let's just show you pretty much in this area. You see you have Paleozoic, passive. Paleozoic's the first era of the Phanerozoic. And this is Precambrian. Okay? And these are Mesoproterozoic, Neoproterozoic, somewhere in there. So you can see you kind of have continuous deposition in places. All right. Now, let's see if they have a stratigraphic column here. Now, in some places you don't. Like here's Mesoproterozoic belt between the Ordovician. That's a great unconformity, if you want to call it that. I think this one has a, okay, thickness, southern Idaho, Ordovician Cambrian. Now, this is important. Camelback Mountain quartzite, I want you to look at this. This is a lithostratigraphic unit. This is what you're going to map in the field. You don't map time units in the field. You map lithostratigraphic units because you have to be able to identify. I can't tell you where the Precambrian, the Neoproterozoic Cambrian boundary is exactly in the field because it's within this unit. All right? I may be able to tell through other methods, laboratory methods, but not looking at it. And lithostratigraphic units are based on lithology, and they can cross temporal borders. Look, here we have one right here. And this goes back really far. into the Neoproterozoic. So we have Neoproterozoic deposits giving directly way to Phanerozoic ones. There's no great unconformity between the Precambrian and Cambrian here. It's not here. All right. Let's see. Let's try this here. Here we go. Australia's another place. So even in North America, where we have the great unconformity and where it was first recognized, it's not continuous, although it is pretty prevalent. It's almost the entire thing. Sequence 1, Neoproterozoic. This will just show you here. So you see the Cambrians within this one too. Deposition was continuous. They don't have any unconformity squiggles here. Unconformities are usually represented by squiggly lines. Australia, continuous. Now, I'm not going to, what's this here? I'm not going to beat this horse anymore. I think you get the idea that the great unconformity is not global. All right, it is not just a separation between the Precambrian and the Cambrian, or between the Precambrian and Phanerozoic. It's not a thing. That is not how it is. And that's the picture they try to get you here. Now, later, they're going to try to fit the Baraboo quartzite into their flood model, I think. See, the young Earth creationists have traditionally that try to fit their narrative with what we actually, within geology, and try to say, oh, geology's wrong. They traditionally put the bottom of the Phanerozoic, that Sauk sequence, the beginning of the Cambrian, at the bottom of their flood. Well, now they kind of are forced to acknowledge these Precambrian sediments, or metasediments, which the Baraboo quartzite is, because they're so vast and thick compared to these Phanerozoic ones. And although I don't think anywhere in this video they flat outright tell you they're trying to fit the Precambrian into their flood model, that's definitely the impression you get. All right, so let's move on.
In that little meeting point, we're missing somewhere around 500 million to a full billion years.
That's pretty accurate for where he is. I'll just let that go.
Years in geologic time. You can see why the secularists don't like talking about the great unconformity.
What? Eric, I just gave a huge rant about the great unconformity and how it's not prevalent globally. I just talked about it. That obviously is a lie because I just did it. All right?
But it's a site that we need to see, we need to get close up on. I say we take our evidence of what water can do from this location.
Water can do a lot. Yeah, it can. And your low flood there. Now they're going to leave the dells and they're going to hang around the Baraboo syncline basically the rest of the time.
And go check out the great unconformity.
Okay, I'm going to complain here because this is a big no-no. When you're trying to do something like this, it's fine if you're just making a movie, but you're trying to supposedly educate people here, Eric. North Arrow. North Arrow. The only time North Arrow is acceptable not to have is if I'm doing this. Okay? Because you know north is to the top. And there is a north arrow here anyway. And I'm going to bust out my geologic map here just right now. These geologic maps, just so you know, that I'm going to do, they're available on my website here under publications. You go here and you can see them. All right. I'm going to try to source everything the best I can. All right. I tried to prepare this a little better for you, but here's Devil's Lake's geologic map. And young Earth creationists don't like showing you geologic maps because in order to make one of these, you have to take your behind out in the field, and I have to walk this whole area and measure every outcrop that I can and try to keep the extrapolation of contacts. Contacts are where geologic units meet. Okay, I have to keep that to a minimum, and I will take measurements, and upon those measurements and the lithologies, what rocks I see out in the field, I make my geologic map, which is what you see here. And just to show you how this relates to Devil's Lake on Google, there it is. Okay, so, and you can clearly tell which way is north because I tell you which way is north. Okay, this is important. Orientation is important when talking about geology. There's some things you always put on a map when making a geologic map. You put a scale, and here's some meters and feet for you guys. I'm going to zoom in a little bit so you can see that. So I put both of them here. And you have your north. These are very detailed things. And you'll see I have outcrops that I take you to here. okay? And measurements, strike and dip is on here. These are your units that I'm using. I explain everything in my legend here. Strike and dip of bedding. That's bedding planes because that tells you the orientation of the rock. Okay, here are my geologic units, and this is pretty standard. Q is Quaternary, C is Cambrian, or C is Cenozoic, my bad. C with a slash through it is the geologic symbol for Cambrian, and X Proterozoic. Okay, so Precambrian to Proterozoic. We'll come back to this later, but I want to get to, okay, let's get that. So, yeah, Eric, north arrows are important, bub. All right, so let's move along here. I love this entrance. Now, there is something here. Like I said, this is where structural geology was figured out. Rock mechanics were figured out in this area in the late 19th century, early 20th century by people like Van Hise and Leith. Van Hise was the president of the University of Wisconsin for a while. Okay? How to predict how rocks relate to one another using structural geology, using methods, measurements in the field, extrapolating that into the subsurface, which could eventually be tested through drilling later and stuff like that. But those methods were developed, the mechanics of mountains, which this Baraboo syncline used to be part of a mountain range. It was created by an orogeny. In geology, we call mountain building event an event. They take long times. We call them orogenies, and the Baraboo syncline was formed through one of those. When something accreted to Laurentia, proto-North America, about 1.5 billion years ago, okay? And we see this happening on the west coast of the United States today. We see this happening in the Mediterranean. We see this happening in the Himalayas. Orogenies happen. They deform the rock units. I'm going to try to use familiar terms, but not layman terms, because young Earth creationists use these terms a lot. And Eric's notorious for this, like his erosion marks in his Grand Canyon video. That is not a term geologists use, and if you Google that, their stuff's going to come up, if anything. And if you type bent rock into Google, let's do that. I will show you what I am talking about. Let's see, bent rock. Bent. That is not a term geologists use. So if you type that into search, you get some pictures. But what comes up? Their young Earth creationist stuff. Canyon Ministries, Answers in Genesis. Okay, there is a place called Bent Rock, so yeah, that's fine. Bent rock layers, evidence of flood. You know, and these are bent rock trails and stuff like that. Young Earth creationist stuff comes up. Now, if I type in the correct term, the stuff comes up that's supposed to come up. Rock deformation. How do we deform rocks? Structural geology. Deformation of rocks. You get the real picture. So I just wanted to show you that. So that is something the young Earth creationists, especially like this guy here, like to do. They like to create terms that geologists don't actually use. And you saying bent rock in and of itself, if you're teaching a 100 level class or trying to introduce somebody to rock deformation, isn't really necessarily bad to use. But if you Google that, you just saw what happened. But if you Google, deform rocks or rock deformation, what comes up is what's supposed to come up. So they like to create these terms which are going to lead you to their stuff, which comes up in a basic search. That's a tactic, that's a dishonest tactic. But it's common among people trying to sell you a bag of bullshit. Okay? Let's move along here. Just one more thing as we go in here, or near this entrance. This is, I forget exactly where this comes in at. There is something called Pompelli's Rule exposed. And I believe I have it on one of my, I believe I might have it here. Pompelli's Rule is, yeah, here it is. It's not right at the lake, but it's up in the trees. Pompelli's Rule is when little structures within a larger structure, the little structures reflect that larger structure. I have S1, S2 here. Those are stress fields. I'm not gonna go into those as zero's initial. Okay, what you can see here is this is phyllite. That's a metamorphic mudstone. And we actually like these in trying to figure out metamorphic things because they, as mudstones metamorphose, certain minerals are created. We can tell the degree of metamorphism better. Quartzites, we can't. Quartzites are pretty stable throughout the metamorphic process until they melt. The Baraboo syncline that's preserved is basically this part right here. The rest of the mountain range is gone. So basically, modern land surface would be right where my cursor is going. Okay? And this is the north limb. We're going to come back to that. Devil's Lake's on the south limb. It's on this part. But I just wanted to show you that because Pompelli's rule, this happens a lot in regional faults. I've taken you to it in my videos in the Upper Peninsula before.
Here it is, number 2, Elephant Rock. All right, guys, we got to head up to Elephant Rock.
Okay, that's it. I am actually impressed he did that. But let's scroll back up here. Elephant Rock is about on our geologic map. It's about right in here. So we're going to zoom in. All right, here you go. It actually outcrops on both sides of this ridge. This is the East Bluff. Eric is going to walk up this way. This is the easiest way to walk up in the entire park. I'm a fat guy, and this wins me a little bit, not even that much. If you want a challenge, you go up this way. Or you park down here and you go up the southeast way, go up the talus piles. But, this is where they're going to take you. And you see Cambrian, that's Parfrey's Glen Formation. We're going to come back to this. But this is about where you are. And see, I have strike and dip here. We're dipping about 15 degrees to the north here on the Baraboo quartzite. The Cambrian stuff, what's the dip on that there? 8 degrees here, and you can see 9 degrees here. The quartzite is 15 degrees here, and it levels out more here. It's not totally consistent, but you can see generally south you go, the quartzite levels out. The stuff here, the quaternary deposits are level. As you can see, this brown Parfrey's Glen Formation, which they are going to misinterpret, or not, they can't even get the unit right, okay? Parfrey's Glen is common throughout the Devil's Lake area, and they're going to get to it, but let's get on to where Eric was ranting.
I can meet Jay. We're going to go over a little bit about what we see there before Steve brings the group up to teach everybody. Here's where we're going to see the great unconformity, an absolute death blow.
Yeah, you'll see the great unconformity there. It's not a death blow, and we'll get into that.
To the secular worldview.
Yeah, he's definitely going from northeast to south here. He's at the northeast corner walking south. That's this East Bluff Trail take. All right, that's from up high. You can see, notice how high up you are here. And let's see, our elevation here is about 13. This is in feet because it's a USGS topo map. So if you want to know what it is in meters, roundabout, divide by about 3. It's not exact. So we're about 1,200 here. So, 400 meters, a little less than that above sea level here. But we're way above even lake level here. And this is conglomerate on top right there of, our quartzite. But it's not always found at that level. As a matter of fact, here we're at 1,200. But see how far down it goes? And it goes into the subsurface here. You can see I have a cross section here. Back here, it goes down. Show you a cross section real quick just to get an idea. See these lines on the geologic map? Those are cross sections. Is that B to B? Because we'll go through that one. If it is, yes it is. So you have to do these cross sections in order to figure out the geology. You take your strike and dip, you take your measurements in the field, and you make a cross section, see if it works. It's A to A prime, that's on the west bluff. Okay, here's B to B. Now here I have vertical exaggeration. This is important to remember. We're on the south limb here. So our beds are dipping 15 degrees at the most to the north. So in order to show you the geology, and the quaternary is so thin compared to the thickness of the Baraboo quartzite, that in order to show it to you, I've got to I've got to give you vertical exaggeration. Here it's 5 times. That means the vertical scale is 5 times greater, but then my horizontal scale, which is to scale, it's to map scale, okay? And that's something we do so you can see the units. And what you see here is you see Parfrey's Glen, this conglomerate they're taking you to at very different levels. And I did use wells. There are wells in the area that I used to verify subsurface strata here. And this is Devil's Lake itself. Okay, so this isn't just surface based off surface data, it's based off subsurface data as well. And we're up on the East Bluff here, and this is about where Elephant Rock is. All right, so I just thought I would orient you a little better there, since we're not just pulling things out of our hindquarters like Eric does.
The great unconformity. How you doing, bud? No, not you, man. Wow, what do we got here?
You're in an amazing location. You're in my home state of Wisconsin. We're at Devil's Lake, and we certainly know that the...
Yeah, Jay giving a lecture. He is completely unqualified to do this. You know, you can be a layman and talk about the rocks. I don't have a problem with that. But he's not a person who studies this. He's not a person who's educated in this. This is not his thing. You know, this is completely inappropriate in my opinion. All right.
The Bible talks about a worldwide flood, Genesis 6 through 8.
That's what we're giving them evidence for.
Is there any evidence? There's a lot of evidence, and this is a...
So these are stories, all right? They were never meant to be taken literally. So trying to do that is actually harmful to the people who aren't like this. You know, the Christians that accept science. This makes them look bad. All right? I know it's a small group of Christians, but they're the ones at the microphone. They're the ones that make the documentaries. The Christians that accept science for what it is and follow the teachings of Jesus, and they don't make these videos. Young Earth creationists do, because they're trying to sell you something. All right? Now, if any of this Babel held water, they'd be publishing papers outside of their community. And that's something else I want to talk about briefly. A lot of these papers in Answers in Genesis, you know, peer-reviewed papers. I've written peer-reviewed papers. Peer-reviewed papers are supposed to be reviewed by your peers. If I'm writing a peer-reviewed paper about the stratigraphy and reclassification of strata in an area, I have other stratigraphers or structural geologists look at that. I don't have a mechanical engineer look at that. I don't have a biologist look at that. That's inappropriate. And there's papers within Answers in Genesis, and I don't know who's peer-reviewing these things.
Really cool spot.
In the middle of Wisconsin. That still blows my mind.
Yeah, and that's the thing. Middle of Wisconsin, like I told you, we didn't understand the why of mountain building until plate tectonics. We most often knew when or had a good idea. We knew the where, and we knew how that was expressed in the earth at present. You know, and that rock mechanics, that the effects of an orogeny, not what caused it, but the effects. What built mountains was not figured out in the Himalayas. It was not figured out in Alaska. It was not figured out in the Rockies in the U.S. It was not figured out in the Alps. It was figured out in south central Wisconsin, Van Nuys, Leith. This is where this stuff, and I think that's awesome. That's probably the main reason why a lot of geologists are taken here, because it's where this stuff was figured out. And they made predictions using structural geology. Van Nuys Rock, they're going to go visit it. We'll come back to that. But these predictions that were made, because back when in the 19th century, there were debates whether the Baraboo was a syncline, a series of faulted anticlines, or some sort of other structures. It turns out there's not a lot of faults in this area. All right, it's a perfect example of deformation, of how rocks can deform. Okay, especially the Precambrian. And structural geologists, you can kind of tell if a structural geologist does a geologic map as composed to somebody who is not. Faults should be reserved for where they're indirectly observed or directly observed when you're making geologic maps. But a lot of guys just draw them in for convenience, and that's not something you should really do. And geologic maps are some interpretation to them. Okay? But this area is one of those areas that's so studied that those interpretations have withstood the test of time, which we'll come back to.
We're looking at a big slab rock here, and then there's something...
That big slab is the Baraboo quartzite that Eric just slapped his hand on.
A little bit different above. Looks kind of...
And the stuff above, where both their eye levels are, above that, this is the Parfrey's Glen. He's going to get this wrong. And I'm going to have to show you why this is wrong. And this is how he doesn't know stratigraphy. He doesn't know how making a geologic map even happens, and he's going to show that. He's going to wear that on his sleeve. But if you're a layman who doesn't understand this stuff, you're just going to roll with it and continue on, because you're not going to know he's wrong.
Kind of boring, but it's interesting, and here is why. Some process occurred to build this rock down.
Let's address that real quick. Some process this rock down here is Baraboo quartzite, where his hands is. Both their hands are. The Baraboo quartzite is a very complex unit in the area, but these purple quartzites, and they're purple for the most part, they appear in other places in Wisconsin as well. They appear, we'll come back to that. They appear in throughout Wisconsin, the Sioux quartzite in southwestern Minnesota. These things are extensive, but they're erosional remnants. Let's talk about one today. The Baraboo quartzite. The Baraboo quartzite itself was deposited as what's called a quartz arenite sand, which means it's pretty much quartz and free of silts and clays, although you do get phyllites in there, which are a metamorphic version of shale. All right, that is a thing. So on top of this unconformity, which consists of granitic rocks, rhyolites, I can actually take you to a place here, in the Baraboo syncline, where there's a black rhyolite. Dark rhyolites do occur. So the Baraboo quartzite was deposited as a quartz arenite sandstone, and it's thick, about 1.6 kilometers thick at Baraboo. And in other places it's thinner, it's thicker, there's conglomerates in it, there are shale units, but dominantly it's quartz arenite sand. Now you might recognize the name on here. All right, this is just published in Terra Nova this year. Now, as that sand was deposited, it was deposited on a tectonically subsiding basin. You're not going to get 1.6 kilometer thick sandstones on something that's being uplifted in orogeny. Okay, so the sand would get deposited, and the sand appears by the structures, the ripple marks, the cross bedding, the phyllite, that it's dominantly either a near shore fluvial stream deposit or shallow marine sediment sand, tidal flat sands. Now, there were stromatolites then, but there were no other fossils, and there's no fossils in this rock. So you have to understand the structure, the structural geology, to make useful interpretations. I can't correlate on fossils. There aren't any. All right, and they try to fit this into their flood model, the Baraboo quartzite. How do you do that with no fossils in it? They have this concept called hydrological sorting, where supposedly the flood sorted out, sediments where you see, stuff that looks like evolution in the rock record, from the Cambrian to today. Things in the water got drowned first, and things on land got drowned, and things in the air got drowned. It's nonsensical BS. But how did that happen here? There's no fossils in this. Back to that. So you got the sand forming, being deposited over an area of Laurentia, Proto-North America, as the basin subsided. We can tell the type of sedimentary environments based off modern sedimentary environments. We have beach sands today. We have sands that lead out into the ocean. We can watch this. This isn't rocket science. We can take drilling cores and confirm this stuff. So we know how this stuff forms. And as this became thicker and the basin subsided, something interesting started to happen. The Baraboo quartzite's protolith, parent rock, is a sedimentary rock, sandstone. That means it's derived from elsewhere. The sand came from somewhere else. You can't create a sediment without sediment, all right? Well, it'll take things called zircons with it as things erode from a distance. Zircons are what we use to do uranium-lead dating, okay? And this is, despite what young Earth creationists tell you, this is a very reliable form of dating. Well, you cannot get an age of the Baraboo quartzite or any sedimentary unit from detrital zircons. Okay, you physically can't do it. All right? Okay, it's not physically possible because you're taking those zircons from somewhere else. What can it tell you? It can tell you some things. Detrital zircons can tell you a maximum age. You can't be older than your youngest zircon in a sedimentary unit. You could be younger, but you can't be older. But it tells us something else too. It tells us source area, which I'll come back to you. But just to give you a sense of the Baraboo here, this is a list of the quartzites that were analyzed and your youngest dates, okay? Now here in the Sioux, we have two anomalously young dates. Now, scientists, we call this outliers, but if I want to be honest in reporting, I'm going to report them to you. They're there, okay? They are outliers. We can disregard them, all right? You can disregard anomalously young points. Because this Sioux quartzite, I wasn't there to sample it, all right? I helped with this. I helped with Thunder Mountain. You know, I think Flambeau, anyway. If you see in the paper, if you see a toonie, it's probably my picture. Okay? So we only get one or two out of dozens upon dozens of detrital zircons, so they're anomalies. But I put them there so you can see that, you know, they're there. Now, based off that, excluding that, the Sioux, this may be an overthick part. This may, you know, there's tons of different explanations. But the vast majority of the data, I can break out a depositional time frame for the Baraboo. So we get late Mesoproterozoic, late Paleoproterozoic. See, the very near the border between the Paleoproterozoic and Mesoproterozoic is when this was deposited. Now there are Precambrian units on top of the Baraboo syncline. You're going to see some in cross section later. They're just not exposed at the surface. They were in a mine, but that has been since been covered, the Freedom Mine, so they're not exposed anymore. A couple are. Actually, the Dake quartzite is in two places. So, see, these are the younger sedimentary units on top of the Baraboo. Here's the Baraboo itself. And here you have the Baxter Hollow granite. For a long time, even when I was a student, we had this question, which came first, the Baxter Hollow granite or the Baraboo quartzite? But now we know the Baxter Hollow granite was drilled into in the 90s, and what's called a paleosol was found on top of it. Not a paleosol, it's a preserved soil. It's not a soil like you think of in modern terms because there were no land plants. It's a chemical weathering profile. The rhyolites are on top of that, and then we get this, and then we get some of these. And this is a good depositional time frame for the Precambrian rocks in the Baraboo area. Now this could be refined later or whatever, but that's based on our detrital zircons. All right, let's get back to this. So we pulled all these detrital zircons, and what was the point of that? Well, here you can see, here's some of the Baraboo, Waterloo, Flambeau, there's the Sioux. Okay, so you see these quartzites are still preserved relatively regionally. And a question was, were these all deposited at the same time? We now know from these detrital zircons that they roughly were. You know, there might have been, you know, deposition may have started in Baraboo before in the Sioux quartzite, but still, it's general time frame. Remember, we do rocks based on lithostratigraphy, not chronology. That's not how we map them. Yeah, this is probably my picture. It's a conglomerate facies of Thunder Mountain. Yeah, it's probably mine. Anyway, so here's our date. We get primary peaks. Distally derived. We're going to come back to this. Let's address it now. When we did this, you see these old dates here. All right? There is nothing in the area in the upper part of these forms that could have sourced these older dates. At least that's our working hypothesis. In the south central upper peninsula, there are some 3 billion-year-old rocks. Minnesota has a couple isolated ones too. But these weren't exposed at the time, and even if they were, they quickly got buried. There was probably, based on what we know and the topography, this is under the Baraboo. This isn't on top of it, which they're going to keep beating about. This is under. There's an unconformity under there too. There was probably 30, so 100, probably more than that. Probably 60 meters, so 200 feet of relief from, you know, Baraboo, Wisconsin, to southeast Minnesota, or even further, all right? So it was not a huge paleotopography during this time. This concept of a big erosional continental-wide thing is not unique to the Great Unconformity, and that's what I'm trying to get at here. But these older zircons, but we don't have anything these ages. So they had to be derived from somewhere else. That's this distally derived. And we did a percentage. The Sioux is more locally derived. And it's the most locally derived of any of them. So it was probably deposited very late in the game. Okay, so 1.5 billion or 1.45 billion years ago. Okay, but lithologically and related to the bigger picture, it is the same unit. Okay, and here's the correlate or cumulative probability plot. So what you see here, Superior Province, that's basically the Canadian Shield. We'll just go with that. The Slave Provinces, Trans-Hudson. Trans-Hudson's mid-Canada, mid-US-ish. This is the Northwest Territories. We have detrital zircons. You can you can determine source area when you get these dates because they had to be crystallized somewhere. Zircons are crystallized from magma, and they're pretty stable, even deep in the earth. Okay, they're not perfectly stable, but on Earth's surface, they're really stable. They only generally get weathered through mechanical weathering, not usually through chemical weathering. So we get these dates here, and from stuff that was from the Northwest Territories. Why is this long ramble you're doing, Steve? Because if our hypothesis is correct, that means this sand sheet was a lot bigger. Did it go all the way to the Northwest Territories? Probably. So you're talking, even though our presently preserved, so you have quartzites here, and you have quartzites here, 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 over here, but the sources are up here. That was a huge sand sheet covering Laurentia long before the Sauk sequence, long before the Phanerozoic. All right? And the only reason why these are preserved so well is mostly because they were involved in this later orogeny. So what happened is the rocks here are Precambrian. We call it the Granite Rhyolite Province because they're not exposed at the surface. So we only have a little bit of information on. They're further exposed further west or in southwest U.S. But there was a compression event, an orogeny from an accretion from this way, from modern south, which created a mountain range here. As you go north, the quartzites are less and less deformed. Okay, so they had to be, but they are quartzites. They had to be metamorphosed first. So this sand was deposited on an unconformity, very thick as a basin, came about. So you had the sand being formed, deposited. Then above that you had some other units. These became buried, metamorphosed. Right? You had to apply heat and pressure to get something metamorphosed. Right? We'll come back to this a little later, in a little more detail. So to metamorphose that, I almost did what they did. Anyway, so you have this unconformity. You have sand being deposited in the basin. You have it getting buried, metamorphosed, and then in the Baraboo area, some accretionary terrain, because plate tectonics, approach from the modern south, creating a mountain range in the Baraboo area, which is now mostly eroded. Baraboo's surviving part of that. Okay, so that happened long before the Cambrian ever happened. You know, the Baraboo's deposited circa 1.5 billion years ago. That's a billion years before the Cambrian, about a little less. All right, let's get back to them. I'm actually going to pause it here. Stop it. I have to go to the bathroom. All right.
Down here, but there's something different up here. The rock above it is different. That's what we call an unconformity. The process changed between these two things. So
see, that's what they do. They give you a little bit of actual knowledge, but they don't give you the whole picture.
Going on? This is actually called Baraboo quartzite, made from sand. It's metamorphized.
The term is metamorphosed, but whatever.
To create the Baraboo quartzite here, and then above it we got a straight line going across.
That is incorrect. The line is not straight. That doesn't have any meaning. Here it's pretty level, okay, pretty flat, whatever, between the two. But there's other places where it's not that way. And like I said, these beds within the quartzite dip to the north, so it should be behind the guy talking, not Eric, behind the other guy. So they dip that way, and this dip's pretty level. It's pretty much not dipping.
Where this rock was actually sheared off, powerful force, and then something else.
Powerful force. They keep saying that as if you need one event to do this. But anyone who's ever stood on a rocky coast with a rocky cliff knows as those waves hit that coast, what happens? The rock falls down. You don't need a catastrophic event to explain boulders.
Started happening to lay down the rest of the layers. What do we have above us? We have chunks of the Baraboo quartzite that were...
That is true. It is chunks. And it's pretty much only Baraboo quartzite, which tells you it's a local source.
broken up. They're sitting here, big boulders. And then we have something in between called Jordan sandstone.
That is incorrect. The Jordan sandstone is not that. It's not how lithostratigraphy works. It's the Parfrey's Glen Formation. It's conglomerate to conglomeratic sandstone. I'm going to show you, like I did in the Grand Canyon, for this area, for the area of essentially the Baraboo Range. Now, it's not perfect like this, but basically what you have here is north. This is your north limb. That's what we're going to take. You see the synclinorial shape, Devil's Lake area. What do you see here? Well, you notice on my map, I don't know if you noticed, there's no Jordan sandstone there. There's a reason for that. Because the Jordan sandstone is up here. This is your Parfrey's Glen. Intertongues with the other Cambrian units in the area. This doesn't propagate outside the Baraboo area very far, but within the Baraboo area, it's very common to see the Parfrey's Glen or an intertonguing with these units because it's a lithostratigraphic unit. It's a sandy conglomerate to pebbly sandstone. And remember, we map units based on their lithology, their makeup. We don't base it off chronology. So while the Parfrey's Glen was being deposited when the Wanawak was, it was also being deposited when the Galesville was, and when the St. Lawrence was, and when the Jordan was. This is the Jordan. The Jordan is pretty much a light-colored quartz arenite. It's rounded quartz, not very much fines in it, kind of like the Baraboo originally was, except this is very friable. These Cambrian units are not as well indurated, and they are not metamorphosed like the Baraboo is. That's why they weather quicker and exhume this paleotopography, if you will. The modern topography is really close to what it was about 540 million years ago, all right, before all this stuff started being deposited. And the erosion has subsequently kind of exhumed that. So the Cambrian deposits and the Ordovician deposits are not as prominent, but they are there. And here is your rhyolites, and here's your Baxter Hollow granite, and your other undivided. So this is your syncline. You see the Jordan's up here, okay? They're at Devil's Lake, stratigraphically. This here, so they're over here. There's no Jordan here. The Jordan's further up stratigraphically. And you map the area, you don't see any Jordan sandstone. This is something I see young Earth creationists doing a lot. It's either intentionally or not intentionally, but they think that geologic units can interweave and be muddled up, and they can't be. Now, if you're going to try to sell a big global flood story, well, flood deposits tend to be jumbled up. They are never produce, nice levels, quiet strata, okay? They jumble things up. And so by him saying the Jordan sandstone intermixed with the Baraboo or the Jordan sandstone, that creates a false picture in your head. It gives you the impression that the Baraboo quartzite is interwoven, if you will, with the Jordan sandstone, which isn't even here. And it's not. That is not a thing. Now, that's not the kind of thing you're going to know unless you are more than introductory level familiar with geology. And we are going to look at a map of the Baraboo area.
So what really happened here is this original creation rock, part of the original creation, hardened. Then when the flood came along...
The original creation, I don't know what that means. Okay, I'm going to assume that what that means is he thinks the Baraboo quartzite, original creation, was created in place as is. Now they're going to allude later that that's not the case. You can't ignore these Precambrian sediments, especially here. So I don't know what they're getting at. So is it pre-flood? Is it during flood? I mean, I don't understand because it's not explained. If you're telling that the great unconformity above that is the base of your global flood, the Baraboo quartzite, any Meso-Paleoproterozoic sedimentary rocks, Neoproterozoic ones, basically just kick through any young Earth creationist interpretation. It can't happen. How can you have sedimentary rocks form, buried, metamorphosed in an orogenic event, eroded, and then have a great flood in what, 2,000 years? So you have to either say, you either have to try to even more fit the square peg in the round hole by somehow trying to put these Precambrian metasedimentary rocks into your already bad narrative, or you have to say they were created in place. Because there's nowhere in the Bible, I think someone would notice these vast basins and orogenies forming within 2,000 years. Someone would notice this. It's not the kind of thing that would... Now, I know from a physics standpoint, it's completely impossible. I get that. We're not focusing on the physics here. Okay? So, this is creating more confusion for you. And that's intentional. And it's also unintentional because they don't understand what's going on.
It came right through here and ripped up this layer, sheared it off like a crew cut.
There's no evidence for that it was a single shearing event. Matter of fact, there's a lot of evidence to the contrary. Remember, they're higher up in elevation. The Parphrey's Glen goes further down in formation, in topography too. And that Parphrey's Glen, I think it's even lower down. So you can't claim that the Great Unconformity is a single shear plane. We have too much paleotopography here for that to have happened, and we'll come back to it later. I'll explain this paleotopography a bit more, but I just want you to understand that the Great Unconformity is not one level global thing. That's the general picture Eric tries to give. He tried to do it in the Grand Canyon. By the way, it's not even level in the Grand Canyon, okay? But they never take you to these places. It's definitely not here.
The sedimentary layers started to form after that with the broken up quartzite, Baraboo quartzite and the Jordan sandstone. This is not only called an unconformity, but they call it the Great Unconformity because we see...
Well, just so you know, too, there are other places in the world I can take you to where there's great unconformities other than the Grand Canyon, where there's completely just, great unconformities within a Precambrian. A perfect example of this is in the Marquette area. You have two-ish there, too. You have very old... some places Archean rocks with Proterozoic ones on top of it. So you got a couple hundred million years missing time there. Between there and the Neoproterozoic, so from about 2.2 to 0.9 billion years of missing time there. Completely within the Precambrian. And then on top of that, we don't know for sure the age of the Jacobsville, but it's probably around 900 million years old. And probably 30-50 million years of deposition. So from 850 million years ago to, there are some Cambrian infillers, to about 500 million years ago, 520 million years ago, you have another unconformity, and that's within city limits of Marquette, Michigan, in the Upper Peninsula. So this whole concept that they're trying to sell you, and I've already explained to you how unconformities don't continue forever, conformities don't continue forever, and I've demonstrated that to you in the literature and in the rock record. This is an incorrect, this is an intentional false narrative. This is a 19th century narrative that we know is not correct. And they keep pushing it, and it just gets me madder and madder, but let's move on.
This kind of thing all over the planet, including...
That's not true. See, and this is the shtick they have to sell you. And they're relying on your ignorance, your lack of knowledge, and plugging it. See, they're not really trying to sell this to people who know better. They're trying to sell this to people either in their camp already or who don't really know. And this is why education is so important. This is why having an uneducated population is bad. Because they're going to go to what they feel as opposed to what they know. All right, that's a talk for another time. Let's move on with this.
The bottom of the Grand Canyon, which you'd have to hike 1 mile down, about 6 hours to get down.
I'll come back to that.
Down there to see this, but we can stand right here in Wisconsin and see the same thing where the flood came through and catastrophically ripped this up and started laying down the first layers of the flood. Bottom of the Grand Canyon, Tapete Sandstone, Bright Angel Shale, and Muav Lime.
Okay. Let's try to bring the Grand Canyon up again. I already got the strat for the For the local area, so the Grand Canyon, all right. He just mentioned, this is that concept that we have the same units over vast distances, which is incorrect. You had the Tepete sandstone, and based on actual science and not pulling things out of our backsides, the Tepetes was deposited about 505 million years ago. Some of the Cambrian in the area is older than this. Let's see. Let's go back to lithology. So you have your Tepetes, your Bright Angel, your mouth. That's what he talked about. He didn't talk about any of the others. Now we come here. We come back down to my Devil's Lake. There's a reason why we don't call this the Tepetes. Why we don't call this the... By the way, the Jordan crosses possibly the Cambrian Ordovician line, but we consider it Cambrian for mapping purposes because I don't think that question's been firmly answered. But we don't call all this the Tepetes. We don't call this Bright Angel Shale. See, you have sandstone, shale, and limestone. That's actually part of a normal marine transgressive sequence. This is a talk for another time. I just want to say when we have transgressing seas, that's the sequence generally seen in the Phanerozoic. We do not even have that at Devil's Lake. This is not the Tepetes. Here we have the Oniota here, which is actually a carbonate. Within the Cambrian, we have a carbonate. I think the St. Lawrence is mostly a carbonate, if I remember correctly. St. Lawrence, is it at Devil's Lake? I can't even remember half the time. No, it's not. That's right, it's not. But it's at the other place we're going, but I think it's a carbonate. I know the Oniota is. This is a carbonate. This is a carbonate. Sand, sand, sand. Sand, sand. There's no shales here. Not dominantly, anyway. All right? So if you're going to even compare it, you have sandstone here, shale, limestone. At Devil's Lake, you have sandstone, limestone, sandstone, limestone. See, this is not continuous. This is a false equivalence they love making. Everything to them can be traced back to the Grand Canyon, and it's just complete BS. And if these were continuous, and we could demonstrate that, we would call them that, but we don't, because they're not. As a matter of fact, let's bring up the Wisconsin. The Baraboo is not on this because this is Phanerozoic biased, like almost everything is. Are the oldest Cambrian sands are about 523 million years old. But here you have the Mount Simon, Eau Claire, Wanawak. This is exposed, these two, now this is a shale unit, into the Illinois Basin, but they're not locally here. All right, these are, and we're going to come back to the Galesville. You have your Tunnel City, and these are your generic, dominant lithology. So, sandstone, shale, sandstone, sandstone that grades into a carbonaceous sandstone. Lone rock, which intertongues into other units. It's a sandstone that intertongues with calcareous sandstones, mudstones, and more sandstone. And you go up more. St. Lawrence, I was right, dominantly carbonate. Your Jordan, you have different members in Wisconsin. In Illinois, they're not. Sandstone. Your Oniota, carbonate. Your Shakopee, sandstone, carbonate. Your St. Peter, there's a huge unconformity between the early and middle Ordovician too. St. Peter's a sandstone. So here you can get a sense of the Phanerozoic rocks in Wisconsin, and some of these can be traced into Illinois and even Indiana. We don't see the Grand Canyon units here, and these are what I usually study. Those of you who follow me know that. But anyway, I'm going to close this out because it's taking up a lot of memory. So this narrative of trying to extrapolate Grand Canyon units into the Baraboo areas is just blatant lying. You can't even claim ignorance. You are telling too much correct information. There is correct information here that isn't unconformity, that kind of stuff, to not know that. This is a lie. It has to be a lie. This cannot be chalked up to just not knowing or tripping up.
Stone, we have the sandstone here and the shale and the limestone above this too.
I just went into a big, huge rant about how you do not.
Just like at the bottom of the Grand Canyon.
And we're a couple thousand
Bullshit. That's a lie.
miles away. Well,
Yes.
a little over 1,500 miles away.
Yes.
Guys, it's really important that you get this concept. We're going to have to teach the whole group this because we want everybody packing a punch
But packing a punch, you mean selling bullshit.
with the unconformity, the great unconformity here. They're not going to come back from this. This is powerful evidence of a global flood.
Just taking a moment. I'm not going to, I already ranted about this. So we're going to skip this guy for now. Let's get to Steve Austin here. He actually does have a PhD.
To see the great unconformity in Grand Canyon, you've got to take, a 7-day raft trip minimum. Okay.
No, you don't. You actually see it with a telescope from up high, but besides the point. I don't know what the point of that is. It's more trying to equate everything to the Grand Canyon. The Grand Canyon is one area. You can't extrapolate a global, what you say is a global phenomenon, off a single area. You can't do that. All right? That's not being honest. If you have evidence that there's a relationship, a correlation like similar sediments, which you don't, you need to be able to show really well that these two are correlative, and they're not. They're not. And they keep trying to do this.
Or hike a mile below the rim of the canyon vertically on a 10-mile trail to get down to the great unconformity. When I see big boulders...
But in his defense, if you really want to observe the rock, you need to take your hiney up to it and look at it. But none of them have a hand lens here. Every geologist carries a hand lens and a hammer with them in the field. Now, you can't beat this rock apart. You can't hammer it. There are other places in the area you can. But, you at least have a hand lens on you so you can see what the rock is made of.
In sandy beds, what's the biggest boulder we're seeing here? 4 feet diameter?
4 feet's a little over a meter. Some of them are actually bigger than that. But I want you to take note of that in the size of these boulders, all right? And that they're very near the source area. That this was probably a lower... when the Cambrian seas came in, these would have been derived locally from the cliffs and just deposited here. That works fine if you have transgressive seas over a long period of time and a subsiding basin. That makes sense because what's high at the beginning of the subsidence of the basin is in a low area later. That makes sense. That's tectonics does that. We know that. We have basins forming right now. The Basin and Range Province in the western United States. But if this was done by a great flood with the topography pretty much as it is today, why is this so high up? Why? With such large boulders. If you had a flood that could do that, why doesn't the Parfreeze Glen, why don't these boulders, I talked about why don't you see small pebbles from far away in this deposit? Why don't you see these big meter-plus boulders sitting on top of the Precambrian in Illinois, in the Upper Peninsula, and all these other places? You don't, because you don't have the energy needed to transport these things that far. There is no global flood.
And when I see boulders and fine sand, that warms.
Just so you know, when I'm talking about global flood, I'm talking about their narrative. That the global flood happened 4,500 years ago within about a year. A lot of people, I noticed this is something I ran across talking to geologists outside North America. They'll talk about sequences like we talk about transgressions, the Sauk sequence, those seas, those Cambrian seas transgressing. They'll use the word flood for that. But flood pretty much means like it does in lay speak in geology. It's an event.
My heart. Because that is pretty powerful, what's going on up there, right? Have you ever tried to move a 4-foot diameter boulder?
Yes.
Not how.
When we get to Abelman's Gorge, I'm going to show you something that has to do with... This was basically talus or talus, however you want to pronounce it, shedding off the Baraboo cliffs as the Cambrian seas came in. And now I've mentioned this before, but I can take you to many places in the world with rock cliffs next to the ocean, and you'll see rocks falling off into the ocean. It happens. You'll see boulders on the ground that fell, on the beach that fell from the rocks. And there is no massive single event to do this. It's not necessary, all right? And we would see other things if that was the case, and we don't.
Not easy, right? They weigh a ton or two. I'm looking for powerful agents, and when I see boulders 4 feet in diameter, that's wonderful. If it could talk, what would it tell?
You're full of it. That's what it would say, Steve. You're full of it.
What kind of story would it tell? Okay, it's an erosion surface within the rock record.
That's correct.
And that's called an unconformity.
Also correct.
And because of the extent of the unconformity in southern Wisconsin, it's called the basal unconformity of the Sauk sequence.
Remember I mentioned the Sauk sequence? That is correct. This is part of the Sauk sequence is actually divided up, but we don't need to do that. This is the base of the Sauk sequence. That is correct.
That's the...
And like it goes into Illinois too.
And so it's a widespread unconformity. Here...
He does say widespread, but I don't know if he uses the word global. Steve's kind of cautious with hanging out with young Earth creationists, but he's still trying to sell the same narrative.
In Wisconsin, down there in Illinois, and then over there in Missouri. And then you go into Iowa, down toward Oklahoma, it's buried, but it comes back up to the surface right near Colorado Springs, Colorado. It comes up to the surface, and in Manitou Springs, Colorado...
They're ignoring so much geology to try to get... They're being very vague, and does not just go down and come up. That's not true. The Great Unconformity does go in the subsurface, but it's not that way. Those of you who follow me know about the Mid-Continent Rift. This is a place where the continent tried... let me bring that up. Let me bring up the... Mid-Continent Rift real quick. Alright, let's just go get you some images here. I ran about this. Okay, this is basically it. The Mid-Continent Rift is a failed rift system in the Mid-Continent North America. This is where North America tried to split about 1.1 billion years ago and failed. This is not an alocogen. This is not a failed arm of a successful rift system. Those are all over the place. This is the most complete, lengthy, failed rift system on the planet. Okay, so you don't, if you live in the American Midwest, you don't need to go to some place exotic to see the largest failed rift on the planet. It's in your backyard. See, a lot of these things, people think you got to go to some magical place far off into nowhere where no one's ever been to see this stuff, but you don't. Anyway, this is the rift, okay? Baraboo is roughly about here. All right, and those rocks, Baraboo, are about 500 million years older than this, because when Baraboo was deposited, the continent ended right about here. Now, it's been compressed, whatnot. And then when it underwent an orogeny, that added from the south here, we think, and that extended the continent to about here. So you had an accretion. So at about 1.1 billion years ago, you had the land to rift. You didn't during the deposition of the Baraboo. But anyway, I want you to see this. This is a failed rift system, because they're going to talk about this later. They're going to talk about the Keweenaw. All right, so that's the only reason why I'm bringing it up now. Let's go back to Austin's Randy Rent. Mine, Brazil. Okay, let's watch this.
Imagine a slurry of boulders moving at maybe 5 meters per second. Okay.
Just address that real quick. You see this debris flow here? Boulders moving 5 meters per second. Boulders can move 5 meters per second, but not for very long. Whatever is pushing this debris flow is going to lose energy quickly. It is not easy. It would take a large amount of force to get this going over any significant distance.
It's 50% sand and boulders and 50% water.
That means nothing. 50% sediment, 50% water fits. I'm not even sure what he's trying to say by that. It just doesn't mean anything, because when you have sediments depositing, it doesn't matter what the water content is. We can guesstimate a little bit on the depth based on the deposits. It doesn't mean anything. All right, that's not preserved in the rock record.
A slurry, a gravity slurry, or something like that.
Yeah, it's real easy to get gravity slurries up on the top of a ridge, isn't it there, Steve?
flowing along of a bottom of a very catastrophic advancing ocean.
Okay, so he's 400 meters, 1,200 feet above sea level there. That is not the bottom of anything. If your Great Flood in the world before the Phanerozoic, if you're using that interpretation, is coming through, depositing this stuff, you're up high. Why isn't that at the bottom of a valley? The only way that you can get that to work is you can't. I mean, you would need such vast forces this planet has never seen. But in a subsiding basin, a localized subsiding basin where seas are allowed to transgress over time, and that high area was a low area, that makes sense. Tectonically, like I've already explained, that happens. We observe that. We don't observe this debris flow in a mine in any large scale. All right? We don't observe this on any... I mean, things don't scale linearly. They don't. And young Earth creationists rely on that basic falsehood to get you to make these erroneous extrapolations.
A flood on the Earth. That's the kind of thing we see here. So I think this is the beginning of the flood right here.
And I think you're wrong. See, and this is going to cause a problem later for them, even with their own, because it seems like they're trying to incorporate later, as you'll see, the Baraboo into the Great Flood myth. Well, if this is the bottom of your Great Flood, how can the Baraboo... You guys can't even straighten this out. You've had just as much time as geologists have at this point to figure this out, and you can't do it. You can't even agree. Consensus is important in hard science. Now, the only way consensus is, shaken up is if a new hypothesis comes along, tested, can't be falsified, then you change that. But you guys have never even formed one. So you're not doing science, despite the story you're trying to tell.
Now, in order to understand the big picture, we have to recognize that the flood triggered an ice age. You can't have an ice age without warm oceans, which the flood would create as the fountains of the deep break open.
There is absolutely zero evidence that is needed to have an ice age. Everything he just told you he made up. You can't take a literal interpretation of the Bible and just make stuff up and say, oh yeah, that means ice age. There's no evidence of that. This is one of those things he's pulled out of his backside. That's not how ice ages work.
And the cooler land surfaces allow the snow and ice to accumulate. The evidence for an ice age triggered by the flood is found in terminal moraines.
Terminal moraines are a type of end moraine. That just means that's as far as the glacier got. I'm going to explain this to you in a little bit here. Let him finish his rant first.
As glaciers advance, they push debris in front like a bulldozer.
That is incorrect. Glaciers erode by plucking and abrasion. They do not act like bulldozers. If they did, they'd be able to knock down mountains, and they can't. Okay? They do not act like bulldozers. That's not how moraines form. You have different type of moraines, but we'll just stick with end moraines, because they're kind of similar in formation on alpine and continental glaciers. So we'll stick with that. An end moraine, let's open it up here, because they're going to start talking about it, so I need to open it up. An end moraine, let's go to IC14. This is the publication. They're actually going to show you some excerpts from this, but of course they don't cite any of it. You see this gray here? They refer to it as Johnstown end moraine. That's fine, okay? This is an end moraine. And the red here is Baraboo quartzite. Zoom out a little bit. So this is obviously a map. So you have your Johnstown moraine. Basically, the glaciers advanced from east to west here. And this is where as far as the glaciers got. That doesn't mean there's no glacial deposits here. That means there's no till deposits here. And this is part of what we call the driftless area on the west side of the Johnstown moraine. Okay, so this end moraine. The glacier was coming from the east, probably slightly northeast, coming in here, and it stops here. It didn't bulldoze all this stuff. That's not what happened. As the glacier moved across the land surface, and I'll just stick with this, it picked up pieces of the foreign rock, of the rock that it went over. And that's why in glacial moraines you do see stuff like distally sourced rocks. You do find boulders of quartzite in moraines that are 300, 500 kilometers away. But you don't see that at Baraboo and in the Parfreeze Glen, because glaciers can lift these things better than water can. So you get your glacier stops here. And what happens is the ice is continually moving forward as the glacier starts to melt. And you may be melting the glacier, but the ice is moving forward at the same rate it's melting back. So you get this temporary stability, and this moraine starts to form because the stuff that the glacier has picked up, and it's throughout the glacier. As the glacier picks this up and moves, it incorporates it higher into the ice. And you get to the end here, and that starts to melt out. So the stuff at the front edge of the glacier starts to get piled in front of it from the bottom and the top of the glacier. Starts to form this end moraine. It didn't bulldoze anything. Because remember, the ice is still moving forward as it's melting. Now, eventually, one of these two is going to win out. The ice is either going to continue to advance past this equilibrium, which it didn't here. After that, it retreated. The ice melted, dropping what's called ground moraine. But he's not going to talk about that, and I'm getting long-winded as it is.
And when the glacier stops advancing, the material or talus that's been collected is called a moraine. So a terminal moraine is the final advancement of a glacier.
That's true. That's fine. But we have things like lateral moraine and ground moraine too.
We find a massive terminal moraine on the Johnstown Ridge.
We came here to find a place where we could see and directly interact with the glacial till.
Just so you know, this is a quarry to the right there in the rock. That's not caused by any sort of natural event over here. He doesn't really say that, but he also doesn't imply it, but I don't want you thinking it is. This is a man-made quarry here.
That comprises the Johnstown moraine. This hump of earth right here is the Johnstown.
Let's try north orientations, okay? Hey, can we at least get that? I know I'm not going to get a scale. Can we at least get a north arrow?
A lot of this stuff was transported the Keweenaw Peninsula copper nugget.
Okay, Keweenaw Peninsula, copper nuggets.
It's definitely over 300 miles of transport.
The Keweenaw, which is where the Mid-Continent Rift is, which is where my cabin is, which is where my mother lives, is about 500 kilometers away. And that's where the Mid-Continent Rift occurred. That's where that is. I'll bring it up again. So he's talking about up here. This is the Keweenaw. Now they're going to zoom out and take you to it, but they're going to not orient it properly. So this is it. And this is copper country. The Mid-Continent Rift as it formed favored copper deposition. I don't want to get into the nuances here because it's not fully understood. We have native copper here. And silver to a minor degree, and gold is lacking, which is really unusual. But I just want to say something about this. Copper nuggets up here have been found that are 23 tons of native copper. Not disseminated throughout the sediments, the conglomerates, or the lavas. A single boulder. Unfortunately now, that boulder not in the U.S. anymore. But typically, it's not unusual to find copper nuggets in the glacial stuff, even in the Keweenaw, the size of your fist.
But the lithologies are various, granites and schists, and it's pretty exciting.
Yeah, the geology of the Upper Peninsula is very complex, very diverse, and that's some of the rocks I study. But notice how he doesn't get in any great detail. He doesn't need to, but he needs to be a little more, he needs to elaborate on that, in my opinion. But just so you know, the Keweenaw here, that's about where Houghton is. It's a little off. Torch Lake, stuff like that. Houghton's actually more like here.
As for the moraine, the terminal moraine is at the end of the glacier. So this is the westward advance. It hits this quartzite prominence and bends around it.
That's not entirely correct. We'll come back to that when they show their map of the driftless area. It makes it sound like the Baraboo formed this mighty stopping thing, but that's not it. At least that's the impression I get from what he's saying.
It plugs the Devil's Lake Gorge on the north, and it plugs it on the south. But the prominent quartzite structure here, we're at about 1,400 feet.
There's some numbers that I can't convert very well. 1,400 is one of them. 426, so 425 meters, plus or minus, all right?
It stops the ice advance, and the moraine wraps.
I don't know what this is. Why are you showing ice in a spinning aerial view coming from the southwest after telling everyone, which is correct, that it came from the east? Don't do this. You may think it looks cool, but it can be confusing to people, especially lay people. And this, I don't know where this came from. I don't even care. It's just bad.
On top of a hill, because this hill was encompassed by a ridge of dirt and the ice.
Geologists don't use the word dirt unless we're making fun of something. Dirt is not a term we use. It's not even a term engineers use. And the fact that he said it, even to lay people, bothers crap out of me. He could have used soil, which isn't, that's more for engineers. It's not exactly correct either, but he could have said deposits, sedimentary deposits. It's, in order to help laymen understand things, you got to use correct terminology sometimes. And you should try to define it, but if you can't, don't use bad substitutes. All right, let's get in here. This here. This is the driftless area here. Sorry, this is in front of you. Okay, the driftless area here, this map. You can see the driftless area crosses state lines. It's in northeastern Iowa, northwestern Illinois, big chunk of southwest Wisconsin, even a little bit up into Minnesota. The glaciers avoided this whole area. The Baraboo quartzite is down here. See where I'm circling it with my cursor? Your ice advances this way. It hit the Baraboo, but it's not like it just went around. All right, the Baraboo didn't stop the ice. This is as far as the ice got. So the Baraboo is not the cause. Something else kept the ice from ever going in this area. This lighter brown color, tan if you will, is older glacial deposits. But the white here is the most recent, what we call the Wisconsin episode. And, you know, the Baraboo did not stop it, you know, in and of itself. I mean, you can tell. There's other rock units here that it also stopped at. So, you know, I want to give you the correct context of the driftless area here. I hope you can see where I'm talking about. Here's Lake Michigan. I know some of you are not familiar with this area of the Midwest, but you can look it up. You can look this up. I'm not sure where this comes from.
Ice behind it, the dirt.
Freaking dirt again! We don't really know why the glaciers never went in this area. Like I said, you get glacial lakes, you get outwash deposits from the glaciers, you get that stuff, but the glaciers themselves did not go in this area. How do we know? There's no diamicton or till, as most people know it as. Van Nuys Rock. Here we go. I do have a geologic map of this area too. And you know, the big one here, this is the entire Baraboo quartzite. There's Devil's Lake. You can see there's Johnstown Moraine. You can actually see the Johnstown Moraine. My map of Devil's Lake does have this. I'm not going to go back to it, but it's that green unit on the surface of the map. And you can actually see it very well from down here. You can see the prominent ridge of it. I want to give you the big picture and the local picture. This is it, I think. Yeah, this is it. This is where they're taking you to. Let me highlight this a little bit and zoom out. This is where we're going. This is the map I'm going to show you. So we've moved from here to up here. See the big picture? See how big this picture is? And we're not even as zoomed out as we can be. By the way, this map is available for free on the Wisconsin survey site, Natural History Survey site. It is Information Circular 14. It was made by DOT. There's an accompanying publication. Someone else is on that publication, but this is DOT's map. And this was done in 1970, and it's still fine. Why? Because he beat feet, he made measurements, he went around the area, and he made observations. I mean, the rocks aren't going to magically change into something else. this holds up. He did a good map. The white areas are your glacial deposits. Behind the moraine, they're mostly till. In front of the moraine, there's stuff like lakes and outwash. All right, it's not, you want to fill in your geologic map. I don't like having white on my map. That's a personal thing. If I've mapped it, if there's white on my map, it's because I didn't map it. That's not the case here. So his white was not the focus. Glacial sediments, river alluvium. But the bedrock was, and that is mapped. Okay, so as you can see, here's my location, my Wisconsin map. Here's my scale. Here's my north arrow. Scale matters, north arrow matters. My legend. This is all the kind of stuff you see on geologic maps. Now, the Baraboo itself is a large syncline, but it has little synclines and anticlines within it as well, obviously, because you can get things like Pompelli's rule being expressed within the rock. And here's the geologic units as I did them. I colored my glacial alluvium and my quaternary. So greens and yellows are quaternary stuff. We're going to ignore most of that. This is going to be our focus here. The Paleoproterozoic, part of the Phanerozoic, and our Proterozoic or Precambrian. They are taking you up here. There's Van Hise rock right there. And we'll get in my cross section here in a little bit, but there it is. Google Earth, just to place you. Van Hise rock. This is an active quarry in the quartzite. It's been there since I've been going up here. There's Cambrian on top of it. They're going to take you to Abelman's Gorge, which I have a little publication on too, and it is part of this map. That's an old quarry that's no longer in operation. It hasn't been in maybe 100 years. I can't track down an exact date. But that's just so you know. So they're going to talk about Van Hise rock here. This is Van Hise rock. This is where so much was figured out. I want you to observe the light color on the right, the dark color on the left. I want you to observe these lines in this here. I'll tell you what this stuff is in a second. And I want you to observe this stuff here. All right, in this fracture pit. Notice how it kind of goes through in places. That's the original plaque. I'm not even sure if you're allowed to climb on this, but I'm not really one to talk and lecture about that. Yeah, because this is me standing on Van Hise rock. You definitely cannot take a rock hammer to this. Do not hammer this rock. Do not sample this rock. This is the one place in the whole of every place I've gone where I beg people not to damage it. You won't usually hear me beg. Here I'm begging. Don't mess with the rock.
Okay,
Erected 1999. This sign postdates me taking structural geology. I'm getting old. Get off my lawn! Yeah.
I'd like to introduce you to Van Hise rock. A whole bunch of geologists started coming by here and started talking about this rock, how cool it is.
It's more than just cool. It's where rock mechanics is figured out in this whole area. But this rock in particular led to one prediction because, like I said, originally before Van Hise and Leith and them, they weren't sure exactly if this was a syncline, a faulted series of anticlines, or some really complex recumbrant fold or something like that. But this rock will tell you that.
Because they see a quartzite mountain that's kind of circular or elliptical mountain, a big canoe structure.
Okay, we'll get into that in a minute. He does give this little thing here, which I think is actually from the publication part of this. IC14, if I remember correctly. You go down, this is the publication. You can see it's there's the director, but it's Dot and someone else. Dot did the map. All right, here's what he's going to stand out. We've gained date information since then, so this is not completely accurate. But for those of you, yeah, here's your Superior Province, Pinokia and Orogeny. I've talked about that many times before. Your Baraboo's down here. And it's the Motzal orogeny, which is a contender, probably what deformed it. But that's not why I'm taking you here, just orienting you a little better. There it is. I think this is what he's showing you. This right here. Let me see. Let me jump back. Yes, it is. But notice how he just shows you the picture. This is a restored dip orientation cross. It doesn't explain it. the Baraboo quartzite. What we have here is what they're trying to do is they're trying to determine using structural measurements, using the cross beds, because you can take strike and dip across beds as well. The source area of this. This was before we had the ability to really do detrital zircon dating really well. 1970, I mean, we could do it, but we get big margins of error.
I've got a guidebook here, and you can see the canoe structure. You can wrinkle it up and make a canoe.
He calls it a canoe. I more call it a deformed spoon structure, but he actually gives a decent description here. Eric's going to cut him off. But I want to show you something about this before I just get into the end of his rant. But we don't need to address most of what he said.
Out of it. And we're on vertical strata. And down over there to the south is the bottom of the canoe. And the other side of the canoe is about 5 miles south of.
That's not a bad overlay. It's off, but it's not bad. This is what you should do. I've done stuff like this.
And that is the Baraboo syncline. Baraboo syncline, that's what it's called. And we're right here on the north side of the Baraboo syncline. And
okay, we'll use this. Actually, I'm going to do this in color because they actually take directly from Dot's map. Like I said, when you generate these maps, you don't just make these maps. What you do is you make adjoining cross sections. He didn't put them on the same sheet. There's no standard saying you have to do that, but they are here. These are the cross sections. This one's a good one. This one, he does no vertical exaggeration, vertical exaggeration. And they will take an excerpt from this publication here you're going to see in a second. So you can see no vertical exaggeration. This is the existing land surface. See this syncline. And here's the Precambrian stuff here. And here's the rhyolites and granitoids, stuff like that. This is what happens when you involve plate tectonics and build mountain ranges through an orogeny. During the time of the Cambrian, this was probably more of the land. This would have been the land surface, actually, down here. So, and you can see the modern land surface isn't much different. Okay, this is where Devil's Lake was on the south limb. The beds were a little shallower dipping then. So you have this here, and I want to take note of something here because I didn't draw it or anything. Synclines, this basically trends east-west. This is basically north here. It's fine. So your axis, I'm going to draw an axis in here. My syncline comes about this. What's that dip? 50 to 60 degrees. This is exaggerated. I forget, it should say, it says somewhere, anyway. It's exaggerated to bring out the Cambrian. What I want you to notice here, Cambrian undivided, that's what we now call the Parphrey's Glen, and I've mapped as that. You see Galesville here. I'm going to talk about it. I have a chunk of Galesville in the geoshed, and it's orange. And it butts right up to the quartzite in places in the North Range. And it's not a fault contact. You normally, if you stumble upon something like that, like between the quartzite, older quartzite, and younger sand, and that's Galesville's highly cross-bedded. And I'll come back to it in a little bit here. You would assume a fault, but you look at it, there's no evidence of fault. There's no slick insides, there's no brecciation, there's nothing. It's a depositional contact because these quartzites stood as islands in an encroaching sea from the south, modern south. So you see that eventually the Sauk sequence did cover, and I believe, is the St. Peter Tippecanoe sequence? It doesn't matter. But you can see eventually they got buried by sediments as the seas deepened. But the seas didn't just deepen. It's not like we had a snowball earth that all melted so the seas came in. This subsided because of tectonics. It was probably really close to sea level to begin with. So I don't want to give the impression that the sea just rose for some reason. We talk like that, but actually many things can cause sea transgressions. Melting ice is one, but it's not the main one. Tectonics is. You get subsiding basins form in response to tectonic stresses elsewhere. Plate tectonics explains all this. And as you can see here in other places, you get little, even though generally a syncline comes back down. You get little ones within, and there's nothing that's fine. you can see that's not exaggerated. This is exaggerated. And these are those younger Precambrian units. And I actually did something about the dake, because I'm in the school of thought that the dake quartzite is not Baraboo. It's part of the Baraboo interval, but slightly younger. I can show you a cross-section real quick. I have it with me. The dake, and I have reason to believe that. The owner of this property was nice enough to let me wander about here. This is the Baraboo. This is the dake. Based off my measurements and observations in the field, this is my interpretation. Or this is not vertically exaggerated, it's to scale. That's my cross section from A to A prime, so A is northish. And you can see here's the Baraboo quartzite, and a little syncline here, but here's the dake. And we know faulting is not really common here, so tight folds can be. Folding is the dominant thing here. You don't need faults to explain this. It works fine if the dake quartzite's a little younger than the Baraboo. Not that much younger, but these units here are these units. Okay, so you have the dake younger. I mean, it's not that much younger than the Baraboo. 1640 million years ago, 1590 million years ago. That's 50 million year difference. It's nothing. So yeah, I just wanted to show you that. Let's get out of that. You can, all that stuff's available to see. This is a general fine thing. Here's your axis, axial plane, from your horizontal. Was that 50, 60 degrees, somewhere in there? Keep that 50 to 60 degrees in your head. Van Heist Rock is here, and this is oriented north is to your left. North is to your left watching this video too with Austin. It's to his right.
We see vertical strata. Okay,
that's true. This strata was originally laid down horizontally as sand and silt, and later buried, metamorphosed, and uplifted vertical. So to give you an orientation, this is younging, this is older. So if these people were around when this was deposited, well, would have been deposited level, and they would have been buried under this. We can call it phyllite, but it's actually just, it's quartzite. It's quartzite. It's just silt-sized quartzite. This is quartzite. This is quartzite. This is more typical of the Baraboo here. This is not. But that's not what I want you to get out of it. I want you to keep looking at these lines here. Let's see if I can get them out.
vertical layers that have been heaved up.
The lines have a technical term. Foliations. He's going to get into that.
What do you need to make the canoe structure? You need north-south compression, right?
And that's true. North-south compression. And look at these lines. So he's deposited level, and they're going to
north-south compression.
And that is the direction.
Build up the layers, the horizontal layers, into vertical
That wasn't a bad animation.
Vertical layers here, and made the canoe structure 25 or 30 miles long, 5 miles north-south.
I've been showing you that. That's from dots now.
So it's a real big thing. Now it's doubly plunging on the east.
Yeah, I'll let that slide.
It plunges down, and on the west it plunges down toward the center of the canoe. So it is really like a canoe. That's the way to think about it. And in building the canoe, the original strata were buckled to make this amazing structure. And so when geologists saw this...
Okay, here we have a little bit of a zoom out. And Eric's about to interrupt him. But this lighter stuff, the pink stuff, that's your Baraboo quartzite. You can even see bedding in it. This is more typical of the quartzite. This is a lens of siltstone. This would not have had these foliations in it originally. This is in place. This rock is not out of place. You might be like, Steve, how do you know that didn't roll downhill from the cliffs? There are cliffs. Steve is facing cliffs on the other side of the road. There are cliffs right here. Okay? But and his lens does not propagate this way or this way. That's how we know it's a lens. Lenses are a thing. It could have been a stream channel or something like that. Here's my cross section. Bear Abelman's Gorge, we're going to take you there. So they're about right up over in here somewhere. So that little lens does not propagate very far, but it is in place. How do we know? Because I can take strike and dip there, and I can take strike and dip here and get the same thing. That's how you confirm it. If I was to take strike and dip here and I got these numbers, vertical, so they're basically east-west vertical, and then here I got something wacky like this, I would know that quartzite can't be in place. This rock cannot be in place because it was deposited later. That's fine. But this would have to be out of place. That's how you check that kind of stuff. Now, all right, any of you ever made a peanut butter jelly sandwich? Ever try to bend it? I don't know if you have. If not, imagine it. What's going to happen to peanut butter and jelly? It's going to move. This is your peanut butter and jelly. This is your bread. This got deformed probably already during metamorphism. All right, remember it's low grade. So something's got to bend. Something's got to flow, compensate. This is too tough to do that. This was too hard. Tough, hard, we'll go with those terms. All right, but this could move a little bit. So you develop foliations. This is not primary bedding. This is later. This is a later deformational structure. Remember that 50 to 60 dip? Now this is pretty level. What do you think the dips on those are? Probably around 50 to 60, which is about the dip of our anticline. Now we would draw it on a line as a cross section, but it's a plane. That's not a coincidence. This happens a lot. It's more complicated than that. There's more stress fields involved. We're just going to go with that. I've taken you to a place in the Upper Peninsula on US 41 where the same thing is expressed in something similar with an expression of Pompili's rule in it as well. So this happens a lot. And that's when they figured out these stress fields, that's kind of one of the conclusions they came to, that this is a syncline and this kind of corresponds to the axial plane. And this would move up and this would move down relatively to one another. You're going to get dragging up here and down here. And it's reflective of the larger structure. That was one of those eureka moments Van Hise, Leith, and others had in the late 19th century. So this is where this was figured out. This isn't just looking at rocks and going, ooh, ah, let's make up their origin story. It's kind of the feel you get from young Earth creationist rhetoric, but when they're the ones actually making stuff up.
Back 100 years ago, they started thinking, oh, I've seen that kind of thing elsewhere. And this became kind of the springboard for talking about foliation. And so
foliation, he does use the word foliation. That's what it is? Good job, Steve.
Foliation was defined here at this holy place.
It was defined, and that's why everybody in the Midwest still goes there. You know, you want to say it's the Mecca of geology or structural geology or this holy place, whatever. I'm fine with that. I don't care.
And exported elsewhere.
Yeah, and then Eric cuts them off. And they figured out the Baraboo was a syncline, and then later drilling confirmed that. So that was the prediction they made based off the field observations and those foliations and bedding. That Baraboo was just a big syncline or big synclinorial structure. And later drilling confirmed that. So you can make predictions in geology. It's not just ooh and ah of rocks.
We had to bring you guys right here to Abelman's Gorge.
Abelman's Gorge, real quick, same map. They were just here. Abelman's Gorge is down here. I'm going to take you, show you because they don't orient you north. But I want to show you something cool here first. This is Abelman's Gorge, right here. Van Hise Rock up here. I'm going to talk to you real quick about the contact between the Galesville and the Baraboo off to the side. Let's do that first before I get back into Eric, because I brought up the Galesville and I need to tell you about it. CWG, before I started putting lines, this is Cambrian. It's not Cenozoic. That's before I figured out how to put the lines through it. We live and we learn. I'm not infallible, but it doesn't matter. I can really use any symbol I want as long as I explain it in my legend, and I did, so I'm good to go. Cambrian, Wanawak Formation, Galesville member. The Galesville here butts right up to the quartzite. This is where the quarry starts. You have a contact here, you have a contact here. Train tracks that you have to cross to get to the contact. Yeah, here's the train tracks. They are still active. That contact's about right in here somewhere. And that's where you meet the vertical Baraboo quartzite right here with the Galesville. And let's go back to my geologic map because there's strikes and dips on that. Just so you know, these strike and dips are mine, and they confirmed everyone else's. That's checks and balances to make sure we do what we do in the field. You can see I have 8 degrees here. The Galesville here, 10 degrees that way. Wow, that's a hard shift. Yeah, because this, it formed around, it was deposited around this Baraboo island during the Cambrian. But it is not marine. At least not right against the Baraboo quartzite. You can see we have Parfrey's Glen here. You can see it intertongues for the St. Lawrence limestone. And I already showed you that in the Devil's Lake one about how the Parfrey's Glen continued to be deposited even as other units were being deposited elsewhere. This is initial dip. All right. And one thing Eric doesn't talk about here, but he likes to talk about in the Grand Canyon video, is that why is the Great Unconformity so level and flat? It's not everywhere. The Great Unconformity, you have initial dip here. The Baraboo quartzite is essentially vertical. And you have 10 degrees to the south here, 8 degrees to the northwest. You go here, and I tried looking for my pictures. I'm sorry I don't have them. I'll probably do another video. Anyways, there's other videos I have on my channel that show you this location. This is a very orange sandstone. It's highly cross-bedded. You look at this sandstone. Actually, I mean, look at the rock. Not just stand point and go, oh yeah, that's cool. I'm going to just fit it into my story. You look at the rock. You take a sample of this. You can sample here. Obviously, there's a quarry. Don't sample Abelman's, but west or east of the river here you can, east of the road. You take the Galesville. Look at it. Look at the grains. It's also a quartz arenite. There are no fines in this. And the grains are well sorted, which means they're pretty much all one grain size. And you look at them, they're rounded really well, and a lot of them have what we call frosting on them. Most quartz sand is somewhat transparent to translucent, but there's like the frosting gets rid of that. It makes it a little more opaque, whitish, if you will. You get that from grains banging against each other in a wind-blown aeolian environment. You don't get that in a marine setting. So the Galesville, what does that tell us? We have frosted grains. That tells us, and huge cross beds and almost no fines. Could the sands have been frosted elsewhere and brought in? Yes. Once you get frosting on sand grains, it's very hard to get rid of. But the high cross bedding and the purity and the well sortedness of this sandstone tells us this is probably aeolian. As the seas transgressed, you would have had beaches in front of these quartzite islands. This was one of those beaches. Eventually it would get buried by marine deposits, but that's what happens in transgressive sequence. You usually don't get aeolian deposits because it's a terrestrial deposit, but you had something blocking it here to preserve it so it didn't get incorporated into further marine sediments. What don't you see here? You don't see any Jordan sandstone there.
Because we're over a half a mile away from where we were at the Van Hise Rock. And here we'll
go back. So I wanted to show you something else I think is cool. Okay, so go for here, Van Hise Rock, Abelman's Gorge. Rock Springs, Wisconsin is where this is north of. What is this? This is where, you see a tinker truck here. The Baraboo quartzite is a real good filter, all right? And it filters water really, really good. Whoever owns it, this Hinckley and Schmidt used to own it years ago, but they backed the trailers up. This was originally a spring. And then somebody bought it, and they backed their tanker trucks in here, and they bottle it directly and charge you $2 a bottle, $3 a bottle, whatever it is these days for bottled water, straight from the syncline. Well, that angered the locals, and it would anger me too. They made a pipe that ran across the way. This flows 24/7, 365 even in the winter. And you can fill jugs up here free of charge and everything. Matter of fact, somebody's parking right there probably to do just that. That's just cool. If you're ever in the area, you can pull off opposite to here and fill water jugs. Bring a lot. It's potable. You can drink it. But he's over here in Abelman's Gorge, and of course doesn't give you any orientation, but I'm going to talk about that here in a minute. Let's go down here.
We see continuous vertical layering. I mean,
This here's your south wall. This is the south part of Abelman's Gorge. This is a bedding plane. We're going to come back to that. Here you're looking at bedding in cross section. There's some remarkable joints and fractures formed in this rock in cleavage. These are all measurements you can take to help you interpret the geology. But we're not going to get into that here. He's going to focus on this, and so am I.
Half mile away, and we're still seeing vertical strata. Over a mile of strata has been uplifted.
Yeah, about 1.6 kilometers in an orogenic event, mountain building event. Tectonics can do that.
This is evidence of incredible catastrophic events.
No, it's not. Not at all. See, now, you have them telling you that on top of the Baraboo quartzite is a great flood. But now he's trying to incorporate this into there, but doesn't really say that. So you can't have your cake and eat it too, Eric. People would have noticed. If they noticed a worldwide flood, they would notice these orogenies, okay, happening really quickly and continents slamming into each other. And they didn't. No one documented any of that because it never happened. So he's trying to incorporate this, from what I can interpreting, into his flood model, but he doesn't say that. This is very misleading. All right. By the way, you're looking south right now. Just let him rant for a minute.
Because there's no way a uniformitarian slow gradual process could make sense of the vertical bed.
I'm just going to not beat this horse. I've already explained repeatedly how this whole thing formed. Give me twitch eye, Eric.
That we're seeing here today. Not only that, you see the ripple marks in it indicating.
Okay, this is the wall. I'm going to bring up this because it breaks my heart. Geologists have been coming here for nearly 100 years, if not more. And I've been coming here too. Where's Abelman's Gorge? I made this in 2015. It's on the website. Topo map, Rock Springs, Abelman's Gorge. You probably saw the title of this. The iconic ripple marks fell between 2014 and 2015. And there's ripple marks behind them exposed now, but they're nowhere near as grand and awesome as they were. A bedding plane failed. How? Well, you can read all this. Here you have the Baraboo quartzite turned vertical, the ripples, frost wedging. Water gets in there. You do have a little bit of a separation forming. The water gets in there. It freezes. In the winter, pushes it away slowly. More so, and eventually it falls and fails. And you create cobbles in this case. Now, this is from 2006. This was the old wall. This is the old wall. 2013, I was there. And you can even see the ripples are within bigger ripples. 2013 as well. There's my buddy Chad on the iconic wall. Now this is before I got fat. This is me in the next picture. And what happened? These fell and formed talus down here. Now, imagine there's a lake here or an ocean here. This talus falls off and lands in the water. Relatively decent analog for those boulders at Elephant Rock being incorporated into Parfees Glen. You have a failure here, and if we had sands in a lake or something, this would be buried with sand as the stuff falls. And then more sand. That's exactly what you'd expect to see. And you can imagine this butting up next to an ocean, because there's places like that. You don't need some sort of global flood to do this. I mean, this took 100 years to frost wedge away, but it failed in a catastrophic event. Young Earth creationists like to use the word uniformitarianism when they're talking about geology. Uniformitarianism is a school of thought. It's not a scientific theory or hypothesis, and us geologists don't really use it anymore. And this is a perfect example of why. Young Earth creationists keep using it, though, and they won't get away from it, because they want to give the impression that everything geologists think happens, we think happens gradually. Well, it depends on your scale. It depends on the amount of time. It depends on things. But we have a uniformitarian type thing going on here. I could say that this rock face, this is the one that fell, this one, this, from a uniformitarianism standpoint, was stable for 100 years. But it catastrophically failed. So it's not one event. You don't need, one catastrophic event to explain how this talus got here, because it happened over a period from when that wall was exposed from quarrying to 2014, 2015, that winter. So it's a matter of scale, and it's a matter of event. This was a single event, and it was catastrophic. We know catastrophe happens in geology, like the Sudbury impact up in Ontario. That was kind of catastrophic. Under the Cretaceous impact, Chicxulub, we know that was catastrophic. All right? We know storms happen. Okay? We know things like this happen. Now, if I step out of geologic scale to 1 million years ago, that happened instantly. But from a human scale, the uniformitarian thing was the frost wedging going on. And then the catastrophe was the failure of that wall. All right, see how this stuff intertwines and can be one thing 1 minute and something else different. That's why we don't use that term anymore.
This was laid down in water, and it's
that's true.
Layer after layer after layer, indicating something happened here. Laid this down by water, and then it was lifted up in a vertical position.
So he's trying to fit, Baraboo quartzite into his flood model. And I've already explained about how that can't happen, how we know how this happened. We know the environment. We pulled detrital zircons. We know that some of this stuff was distally sourced. So this was a much more extensive unit long before it was buried and metamorphosed and underwent neurogeny. This does not fit into your flood model. Now you've got trying to incorporate something like this into a 1 year event when you already had a problem with it doing it with the Phanerozoic. And like I said, there's no hydrological sorting here for you to fall on, Eric, because there's no fossils. And while this was being deposited, a little later, the Belt-Purcell group out in Montana and in Canada would be deposited. A little after that, the Sibley group, which isn't as thick, would be deposited on the north end of Lake Superior. Before this was deposited, you had the Huronian supergroup being deposited. So you can't explain all these things in these different environments. By the way, the Huronian seems to be a passive margin sequence. This seems to be an intercratonic basin series of sands. So you can't just try to incorporate all this stuff into 1 year. The Earth would not survive this, Eric. It wouldn't survive this if it took 1,000 years. If it took 100,000 years. You can't do this in 1 million years either. Earth wouldn't survive this. It's kind of like, all right, you take your hands. We're going to do a little tectonic analogy here. Picture two things rubbing against each other, a fault plane or something like that. Move it slowly. What happens? Your hands together. You can do it, no problem. Now rub your hands together really fast. What happens? You generate heat. The faster, the less time it takes to do something, the more heat you're going to generate. The more heat you generate, it can't go anywhere. So what do you think is going to happen to your global ocean as this heat builds up, Eric? It's going to evaporate. And then the rock's going to start to melt. So them trying to incorporate this even further into their narrative just really works against nature, laws of physics, anything we know. Do we understand the natural world completely? No. Is my view of the Baraboo syncline and other geologists' view 100% correct? No. No, but it explains what we observe. We can make predictions. Your flood predicts nothing. And just another thing, too, the detrital zircons real quick. Another thing, if they were honest about trying to talk to you about detrital zircon, like say, they like to sit there and bash on radiometric dating, but it's all done from argumentative standpoints, and in science, arguments are starting points. They aren't evidence of anything. You can't argue your way out of data. You can't argue your way out of a working scientific hypothesis. That's fine for philosophical debates, but you can't do it here. Basically, you have to be able to put up or shut up. And if you can't put up, then you shut up. You don't just start making stuff up, which is what Eric does. We'll visit here. You'll get a source for this. All right, ResearchGate. I'm on here too, by the way. Let's go. So this is what we're looking at, because what I need to show you is this here. We pulled detrital zircons what happens is we get a spread of ages. Notice how you get peaks and troughs and gaps, and then nothing. You get to a certain point and where you don't have anything. You see how this stops at 500 million years? There's a reason for that. That's because they don't have any zircons younger than that, okay? Why do you think that is? Well, it's because that's as old as this can be. Now, if you had some sort of globally derived sediments, on occasion, you are going to get, and more than on occasion, you're going to get detrital zircons of every age. You're going to get them from, it only goes back 3,500 million years, but you're going to get them back from 4.5 billion to 0, essentially. If you wanted to fight against uranium-lead dating and propose a hypothesis to the contrary, this is what you would have to do. You would have to sit there and say we should find a more uniform level graph from detrital zircons, from these sediments, and you don't. We don't find 50 million year old detrital zircons in this. If we did, that would be a problem. Is it a problem we find 3,200? No, that's not a problem. You just can't be older than your youngest zircon. So if your youngest zircon is here, that's your maximum age. You have to be younger than that. So in a young Earth creation, if they were actually honestly interested in giving you a model, so you would see a more level distribution of detrital zircons in almost every sedimentary unit, and we don't. You would have preferred peaks, but you wouldn't see this, and you definitely wouldn't see it end. That would be a way to check this young Earth creationist claim using actual methods of science, and they don't even propose that. There's reasons for that, because they know it's BS.
And this is happening for miles. This isn't possible.
I need to clarify something here. When we're talking about the geologic thickness of a unit, when we say thickness in geology, we aren't talking about, height, exposure. We're talking about the thickness of the unit as if it was deposited in its original setting. Now, obviously, some things don't have thicknesses that are easily measurable, like granitic plutons. But lava flows do, sediments do. So when we are talking about thickness in these type of things, we're talking about thickness from the bottom, the oldest bed, to the youngest. This is our thickness. This is not our thickness. Thickness works pretty well if the unit's pretty horizontal like it is here and here. But when you get deformation, it's not. Thickness is not this way. It's not this way. It's from the oldest to the youngest. Same here, oldest to the youngest. Now we have more compression here, so we're probably closer to the nose here. But that's your thickness. It's not this, okay? It's not the whole bloody thing. It's not the thickness. It's not the distance from here to here. It's not that.
So in the uniformitarianism geology that has been presented to the world today, it's only possible with a massive catastrophic event. Not only that, as these vertical columns go up,
it's not columns, it's bedding.
The vertical layers go up, they're then sheared off at the top, and on top we find a brand new set of horizontal layers.
Yeah, this is the great unconformity. It's on top of this again. Nothing new here.
Layers of sandstone, indicating...
Yeah, I'll show you the geologic map at Abelman's Gorge. Now, here is Abelman's Gorge. We get some Parfrey's Glen, but we also get some Galesville. And our Parfrey's Glen tongues into this. Why isn't the Parfrey's Glen all over everything here? I mean, it's right near where you'd expect it to be. Near these quartzite hills, prominences, if this was deposited in a transgressing sequence during the Sauk sequence. In some places it's absent. This doesn't contradict anything, our models, at all. At all. Oh yeah, see here, this is how you do it. You take measurements. Here's your S initial, your S1s. See how the axial surface aligns with our foliations? And that's what leads to the predictions. All right, this is not simple stuff. This is why a geology degree, a bachelor's, requires calculus. These are stress fields. As things get compressed, circles get deformed into ellipses. Let's talk for another time. These are stereo nets. These are those projections I was talking about that engineers also use. Here is actual microscopic analysis of the rocks and looking at the rocks, something I have yet to see anyone in this video do. Here's cross beds that you find in the area. Okay, this is the cross bedding, cross stratification, trying to determine where the stuff originated from based on those. It's not going to give you strike and dip of the regional trend, but of the local cross beds. This is the Baraboo Hills. I don't know why it's turned this way. I thought there was a north arrow. Hypothetical. I think it tells you. Rotated 90 degrees. Cambrian north is to the right. Modern north is to the top. All right. Let's see if I can get to it. I know it's in here. I'm pretty sure it's in here. Let's go a little further. I'm trying to cut off. Oh, here's the end moraine. This has to do with the glaciers. So here's Van Hise Rock. Now, they were facing opposite ways. That's why you didn't see this. This is looking west. When Austin was telling you in front of Van Hise Rock, behind him was east. And this is the depositional contact. Now, there is a little bit of vertical exaggeration here, but you see, this is the Galesville. This is your initial dip. Even between units, there's initial dip. Notice the Galesville is here, and the Parfrey's Glen is on top of it. Because this unit intertongues, and it continues to be deposited through other units. And here, it's on top of it as well. You do get some boulders in it. In some places, they're completely absent. So here's your Van Hise Rock. This polished outcrop is cool. It shouldn't be polished, and it is. We don't really know how it got that way, but it's just one of those cool enigmas. All right, so your breccia zone, and here's your cleavages, and your cleavages match the cleavages in Van Hise Rock. So we're just going to end that there. I just wanted to show you this is not just stuff. We don't make these models based off whimsical intuition, Eric. Parfrey's Glen formation. Oh, just so you know, the Parfrey's Glen was formalized in, I think, 1990. That's the earliest date here. This, 1989, but one of the references is 1990. That was about 5 years after we had the North American Stratigraphic Code.
Massive amount of water came through here, sheared them off, and redeposited sandstone. We're not talking a local event here. This is evidence of
Exactly what happened. If this was global, I would expect to see Baraboo quartzite cobbles at the bottom or right above the Great Unconformity throughout North America, and I don't. I would also expect to see granitoids from Canada, greenstones from Canada, ironstones from Upper Peninsula, in with this Baraboo quartzite, and I don't. Not to mention the Detrital zircon thing. These are all ways to test your claims, Eric. Why don't you put forth a testable model? Because you know if you do, it will fail. So what you do is you take people to these points and you just look at things and argue something that is not the case. And you'll sprinkle a little bit of actual geology in there, but then you come to a whimsical conclusion not based on anything. 150 years of geology is behind this. And in order for something to last that long, it's got to be pretty solid. And we will discard things in science if new theories and data comes up and the old stuff doesn't work. We'll revisit it. We don't just sit there and make this stuff up. It's not like in 1850, a bunch of guys got together and said, hey, we're going to disprove the Bible. We're going to make up a bunch of things about rocks just so we can sit there and make God mad. That never happened. And I'm not bashing religious people when I'm doing this. I'm bashing young earth creationists when I do this, because that's the thing they try to do. You saw at the beginning of the video. Eric was doing it at the beginning of the video. So this isn't something people did, all right? We came to these conclusions. This is where the evidence led us. This location, let me see if I can find it. This was an active quarry when I was a student. It was an active quarry for a very long time, and it's kind of a replacement for where you can go since the cool iconic ripple marks fell. It also is on the north limb of the Baraboo syncline. So the rock trend is not much different. This might have been that quarry they visited before. Or that might be LaRue. I don't know. I don't remember everything. I'm not infallible. All right, here we are. Here it is. Okay, this was an active quarry when I was a student. It no longer is. It is now a natural area. You go in here, you park, you walk up to it. This is bedding, still vertical here. Okay, and this is where they're taking you to.
Hey guys, it's really great to be here in the narrows of the Dells. This is the very tip of the canoe of the syncline. It's kind of just...
It's up here. I think it's right here. I think this is it. Let me zoom back out. So it's right there. 90, Baraboo. Yeah, I'm pretty sure it's right about there. So let's get back. I never did a map of this area, so I don't have it at the ready. We're looking about right here. Let me zoom out so you can see that. You can see that's like due east, basically, of Abelman's, and Van Nuys Rock's a little bit north, but okay, there's where we are. This is how you actually orient yourself when you make these maps. This was real hard before we had GPS and phones and cell towers everywhere. It's made it a lot easier. But making geologic maps, even in the 70s, 80s, and 90s, basically by hand. We have software that can do this. We can walk contacts and have it do it for us now. But back then you didn't. You did it the old way. You took a field map in, and if you didn't know where you were and you drew a line, it was wrong. Someone's going to call you out on it when they went to use it. So you did the best you could. Township and range was used. It's an abandoned system. We don't use it anymore. So you had to have your stuff together. You had to know where you were to make these things. Walking around at random points doesn't help you. So you can see here from Dot's map, we have roughly east-west strike, and we're vertical. So that's about where you are. It's in this area right here.
Of the Baraboo quartzite. Because up in the top of the hills here, we have the very lifting up of the rock again, where we see a vertical uplifting of a...
These ripple marks are awesome right here. You can't easily, at least I can't, I'm too old and fat, so I don't try to walk up there. I stuck to the west here a little bit when I did my video, but you see these in my video, and I so wanted to get to them. But remember, this has been turned, so our dip is essentially into the ground. We're vertical, but our strike is this way. But you see these ripples are oriented differently. We have a little bit of a different depositional environment here. We're going to talk about that. He gets it wrong.
Lake bed. It's an...
That's wrong. This is not a lake bed. I don't know of any lake that can deposit a mile or 1.6 kilometers of quiet water sediments over an area of several states. This isn't a thing. Now, you can sometimes get a series of interconnected playa-type lakes and stuff like that over time in a subsiding basin, but there would be evidence for that. You don't really see that here. What you do see are these ripple marks, which indicate flowing water, and I actually go through this in my video. What we have here is we probably have a tidal flat environment. So when the tide would wash out, you would get little streams forming, creating ripple marks. When it would come back in, same thing. So you can kind of tell that deposition, that at least trend when this was deposited level, was basically from up here down here. Now, if you were to flatten this out, this would be north, so this would be northwest to the southeast. This is probably a tidal flat to nearshore marine environment. This is not a lake. That's just ridiculous. Except for the detrital zircons and whatnot, we now know that the other quartzites through them out the Midwest were likely deposited around the same time. All right, plus or minus. This would have been one massive lake. It's just wrong. And I'm not even going to say he's lying. I don't think he knows. So he's just wrong.
It's an amazing thing of the power of God to lift this very thick platform of Baraboo quartz.
Notice he says power of God. He doesn't mention a flood. See, that's ambiguity. You can't do that. You can't sit there and have people tell you the great unconformities where you think the boundary between where God created things in situ, and above was your flood, and then take the stuff below with that in situ part and say God's power. Is this part of the flood? Is this not part of the flood? You can't even say that, let alone produce a model. These guys are not doing science in any way, shape, or form. They're doing that point argument. They're taking you to specific spots, alluding to the big picture, but not telling you the big picture, giving you no sources, and they're just talking. No one's looking at the rock or anything like that. But he's not a geologist. He's talking about the rocks, and it's inappropriate. And Eric should know better. I'm not going to blame this guy. I'm going to blame Eric, because Eric should know better, but he doesn't care.
What a great place it is to see.
See what Dennis Seiler is, Executive Director of Living Waters Bible Camp? What does this have to do with understanding geology? Nothing. All right, Dennis, I'm going to leave you alone.
So get to see the beauty as well. So when we see the very
beauty is in the eye of the beholder. It's not a tangible thing. I think it's beautiful too. Somebody might think this is ugly. You know, it doesn't mean anything. To talk about the beauty of something is irrelevant.
Vertical, to realize that they were laying horizontal one time at the very base of a lake.
You got the horizontal part, but it's not a lake.
And then they were metamorphized.
Metamorphosed! Come on!
They were heated up and lifted up, and as they lift...
Okay. Yes, heating is part of the metamorphic process, but that's a bit ambiguous. Heating makes it kind of sound like it was really heated, possibly even, melted, but it hasn't. It's all metasedimentary. All right, I'm going to take you through this. This is from one of my books. It's from the actual lab one. If I made this, if you want to, this is in-depth geology here to identifying rocks and minerals. You got to have a firm understanding to begin with. It's basically you got to have a lot of experience to use this. A lot of things that you learn from doing, not memorizing, stuff like that. Let's go here. Where are you? This is the kind of thing you produce when you actually look at the rocks and don't just make stuff up. Let's go here. Generally, when I talk in my lectures, you have lithification, diagenesis. That's the rock becoming from sediment to stone. In lithostratigraphy, we don't really differentiate the two. We don't care if something's underrated or not. Diagenesis, low-grade metamorphisms here, your medium and your high. That's usually the terms I use, but these are the correct terms. Then you got these here. See, this is why we like mudstones. Their metamorphic path goes to slate, phyllite, schist, gneiss. Now, almost any rock will eventually become more gneiss if metamorphosed enough. But up to here, and a lot of sandstones can become schist. We can see this pretty well. And I'm showing you this because here is your pressure, kilobars, about corresponding depth in kilometers. It's not always the same everywhere. Your temperatures in degrees Celsius. Now, different rocks melt at different temperatures. This here, basically, if there's water present in the rock, you can melt the granite before it should melt, if it's dry. That's your melting curve. It gets kicked up. You can see granulite facies here, migmatites. Generally, most quartzites fall somewhere in here. They don't really go into here. There's a couple, and they almost never go into here. And if they did, they would lose their primary sedimentary structures like ripple marks and things like that. So Baraboo is about right in here. So it had to be buried pretty decent. Even though it's 1.6 kilometers deep, thick, it had to be buried about 10 before it even got deformed. So the preserved Precambrian sediments probably aren't even all of them. That's how that works. So if we had high-grade metamorphism here, these wouldn't be there. And quartz, pretty pure quartz rock is going to melt relatively low temperatures too. Talks for other times. Let's move on.
They were very ignorant, especially when you consider they were living to be several hundred years old.
Mm-hmm.
They were living to be a lot older, lots.
I'm going to skip this. You can tell he's getting annoyed too. So. Parfreeze Glen, let's open that. I'm going to try to be a little more brief this time. I did do a geologic map of this too. So here's what you're looking at. As you can see, there's a little bit of quartzite exposed, but vast majority of it's not. Once again, your Q, that's your quaternary stuff. It's not relevant to what we're talking about. Parfrey's Glen and the Baraboo is pretty much all you see here. This is a recent exposure. This was not here. I think there was flooding in like 2012 or 2011 that exposed this. Changed the course of the creek, exposing it. We're going to focus on the Parfrey's Glen here. And as you can see, I learned how to put the slash in by this time. So, okay. So now you have your map. Let's go to a cross section. I had to do vertical exaggeration here. So 8A prime is basically from north to south. So we're just going to look at that 6 times. Okay. Absorb that. Oh, this is based... This dash lines like this, question marks, that's you're not sure. There was a well in the area that kind of alluded that it was there, but I wasn't sure. So I just added it because the well showed evidence for it. But I'm honest about my ambiguity and not knowing.
In southern Wisconsin, and we're looking at the characteristics of the sandstone, trying to understand.
Remember how I said you can get initial dip in rocks? Here they look relatively level, but they're not. You still have a little bit of initial dip here. This is the type section of the Parfrey's Glen Formation. This is it right here. That was formalized in 1990. I showed you that real quick too. Austin actually does a decent job here. He does mess up on a couple of things. But let's watch it. Let's get to it.
How the sand and the cobbles and boulders were deposited together in this very unusual canyon. What I see right here are these quartzite class.
Yes, you do. You see lots of quartzite there. Parfrey's Glen has Baraboo quartzite in it by definition. But I want you to notice something. Where is Parfrey's Glen? We were just here. Parfrey's Glen. We were just here. You know, Upper Narrow, Van Nuys Rocks over here. Let's try doing that. Yeah, see, Van Nuys Rock. We were over here. Where's Parfrey's Glen? Devil's Lake's down here. So it's almost due east, but it's a good distance from it. And that's important. You walk up here. The trail eventually becomes a creek. You can't see it here, but there's so many cliffs here. It's awesome. Anyway, okay, so this, just so you know, it's about due east. Back to go.
Big cobbles that are...
Yeah, they're smaller than those massive boulders at Devil's Lake, aren't they there, Steve?
Supported by sandy matrix. It's matrix supported, not class supported.
Yes, that is true. Good job, Steve. You did well. Oh, I need to open one other thing here real quick. I need to open my book again and get to sedimentary. My book is copyrighted stuff, but I wrote it, so I'll show it to you if I friggin' want to. By the way, this is pudding stone. He's going to bring that up. This is pudding stone in Ontario. It's Lorraine quartzite. Look at that jasper in it. Okay, conglomerate. Here we are. Conglomerates with matrix. Matrix is basically, I actually did a georan on this, anything that's not granular sized and coarser. So not your granules, not your cobbles, pebbles, boulders, or as engineers call them, gravel. So this is not a conglomerate. This is mudstone or silty mudstone. This is not that. So this is fine for conglomerate, muddy sandy conglomerate, depending on the matrix. But you can have class-supported conglomerates or matrix-supported conglomerates. Matrix-supported at Parfrey's Glen. The boulders at Elephant Rock at Devil's Lake are class-supported conglomerate. They're just boulder size. But we can divide conglomerates further other than just based on class size. We have paraconglomerate, orthoconglomerate, and diconglomerate. 3 main types. These 2 subtypes, this tells you what it can be. So you use oglometric and polyometric. Those are reserved. Oglometric is for conglomerates whose class are greater than 80% one rock type. Polyometric is used for class less than 80% of one rock type or multiple varying lithologies. So the Parfrey's Glen is an oligomeric paraconglomerate. It's all Baraboo quartzite, which you can see is some degree. Orthoconglomerate is class supported, but alluvial fans are another one. And these are basically low-level alluvial fans is what you're looking at here.
Where the individual large rock fragments are not sitting in contact. That means that this froze very abruptly.
We don't use the word froze. That's not something we say.
and it created this unusual texture. We call it pudding stone. Now,
Pudding stone is not a term we use in geology. It may have been in the past. No one says that now. I just showed you pudding stone from before. It's a rockhound term, is what it is. It's a matrix-supported conglomerate. Just go with that, Steve. You don't need to interject pudding stone. I mean, whatever.
which is a good way to say it. But it's a pudding stone texture, and we see it throughout the canyon here. See the pudding stone texture. And in between we see the sandstone layers. Up here we have another pudding stone.
See, you can see this is actually almost class supported. These big things that are classed. Notice it's all Baraboo quartzite. Notice they're smaller than they were at Devil's Lake. The quartzite is underground here. It's not against cliffs like it was at Devil's Lake. These are more rounded. These aren't angular boulders. These have been transported.
And we even get larger boulders in here, in places 4-foot diameter boulders up here. And
you do get some bigger boulders. That does happen. But we'll come back to this in a minute.
And again, they're matrix supported, not class supported. And they're rather angular and sometimes tipped up at...
They're angular, but they're also more rounded. As you get further from the quartzite, you do get Baraboo. They generally get smaller and smaller. There's other places and other sandstones, they're perfect, or not perfectly rounded, but they're really rounded. There's no such thing as perfectly rounded. They're really rounded, and they're barely even there. You see them on occasion. You see them, the white sandstone, these little purple bits sticking out. The further you get, why do you think that is? That's because they've been transported further. If this was some sort of catastrophic stripping off of Baraboo quartzite extent, I mean, we're further from the syncline, but we're not that far from the syncline. We're actually on it underground, but underground it's still there. But from Devil's Lake, we're not that far from it, and you're actually lower in elevation. So the Parfrey's Glen goes down to about, what is that? 1,100, 1,000 feet, 300 meters. So it's lower than at Devil's Lake. Okay, so your conglomerate here, there's a reason why this happens. Now, in a big slushy 50% debris, 50% water model, like you showed in that video earlier, I would expect this to still be jumbled up. If your flood was that powerful, why aren't there big, huge angular boulders? He's focusing on the few that are angular, but look at the ones that aren't. And these are actually sub-rounded. They're still rounded. And where's all the stuff from far away? It's again the granitoids, the biffs, whatever. Why isn't this here?
Angles indicating they froze rapidly. And so
we don't talk about sediment using the word froze. He knows this. I'm not going to let him get away with that. Clasts don't freeze in sand. It's not what happens. The clasts were deposited within the sand. And this is not Jordan either. It's Parfrey's Glen still. We're still stratigraphically way below that. And this is where the Parfrey starts to give way, intertongue with other units, because you're getting away from that source area.
Individual sandstone beds with these cobble layers in between argue for rapid deposition, matter of minutes.
No, it doesn't. It does not. Here, I'm going to show you something here. When you actually look at the rocks, see, there are some bigger cobbles. He said 4 feet a meter. I don't remember seeing any that big. These are not boulders within the Parfrey's Glen. These are boulders of Parfrey's Glen falling out. So these are not, I don't remember ever seeing any meter ones. Maybe there are. But basically what you have here is you have a coursing upward sequence on occasion. You get that in alluvial fans. You know, granted the dip is very shallow here, 7-8 degrees, but it still happens. And you have evidence of storm rip-up deposits. See, so you'll get conglomerates, matrix supported, you'll get sandstone, then you get a little bit of conglomerate and lenses, then you get more conglomerate, some places. See, it's very well bedded. It's for him to claim, which he's going to do, that it's coursens upward. It doesn't. I would not draw a cross-section of this canyon with little pebbles down here and big boulders up here, because that's incorrect. This is what you see.
Not millions of years. So as we're studying this outcrop...
That's an interpretation based off nothing, Steve. Nothing.
We're becoming catastrophists.
No, we're not. No, this is not the kind of deposit you see in a catastrophic event, let alone a global one. This is not what we would see. Where's the scour pits? Where's the jumbling? Where's the detrital zircons, from 5 million years to 4.5 billion years in this rock? Stuff that your global flood would demand we see, we don't see. There's nothing catastrophist about this. With waves and depositing, beating up those Baraboo cliffs as they became more and more buried, and the smaller stuff, obviously waves can take smaller stuff further out. Obviously, you need less energy to transport smaller particles. You need a lot of energy to transport boulders. Steve, where are they?
Our way of thinking about the process of sedimentation, and this really shows it well. And I love thinking about mud flow here. Mud flows depositing all of this, these cobbles and sand very rapidly. Let's talk about the strata we see. We call them cobbles. And the cobbles are in that one layer. And as you look at the texture of the layer, you also want to look for sorting. What sizes are in those layers as you're going?
And sorting is important. And we know what physical processes can sort rock and grain size and stuff like that. We know this. Look at how level these beds are. Look how thin this is not something a global flood would produce. Even at this scale. I'm not even talking about all the shales and all the finer sands and siltstones and intruding rocks that have been dated into the Phanerozoic rocks. Even here, this is not the type of thing you expect to see in a global mud flow, Steve. Whatever, debris flow.
Going up. Are they well sorted or poorly sorted? And
depends on the bed.
And how are they structured, layered on top of
this? I love this. This actually, a chunk of this fell. This stuff is fractured. So it's down at the bottom now. I think it's even in my picture. I think it might be in one of my pictures. Oh, actually, I think it's just out of sight here.
Each other. As we go up, what happens? We're seeing a coarsening upward sequence.
Like I already touched on, you can get those in alluvial fan deposits, which you would expect if this was near shore but marine. Level alluvial fans aren't something to not be expected. Coarsening upwards happens, but it's not consistently coarsening upward. He's giving this kind of false impression that it's very like boulders at the top and fine sand at the bottom or sand at the bottom. That's not what happens. He's even showing you that's not what happens. And yet he's saying this. You get beds of conglomerate within the sandstone and vice versa. So this is not alluvial fans with streams and tides and marine storm rip-ups and transgressing seas. This is what would make this. All right, we don't need some weird, bizarre way to explain this.
I see a lot of sand at the bottom.
Here's your sand. Here's conglomerate. Here's pebbly sandstone. Conglomerate. This is all sand, Steve. A little bit of pebbles here, sand. Pebble. Matter of fact, the further you go up, you do get occasion coarser cobbles and boulders, but you get more sand. And it's dependent on the unit.
Boy, I'm seeing some big boulders up there near the top. Looks like the process is first it's laying down cobbles, then it becomes boulders. When we see the texture,
what you would see if you had a massive debris flow flowing over the landscape is this would all be jumbled up for one. You wouldn't get neat, nice bedding. Now, eventually the waters would calm down and you would get settling out of sediment. But we wouldn't see coarsening up sequences in that type of environment, ever. I don't see how you could, not unless something re-agitated your floodwaters. But you don't even have a model, so you can't make these connections.
Of all kinds of cobbles that are floating in a sand matrix, we have a name for that kind of rock. Pudding stone.
No, the name for that rock is a matrix-supported conglomerate, or a sandy conglomerate, or in this case, what was that? Oligometic paraconglomerate is the technical term, I think. So you're wrong, Steve. Pudding stone is not a rock type. You'll never see that on a classification chart. But he should know better than that, especially as being a person of authority. I don't know everything about geology either. But there's just some basic stuff they seem to get wrong a lot, and this is one of those things.
A pudding stone is and then halfway up the cliff, we're seeing some pretty good size.
What you probably have here is some sort of local unconformity. There's nothing weird about this.
Matrix. And then the top of the cliff is sandy, isn't it? When we're coming up here, one of the ladies asked, how do ripple marks get buried in the quartzite? The answer is they get buried in the quartzite from fluctuating current velocity. That's the...
I don't know where he's getting this from. The ripple marks got buried in the Baraboo quartzite, and even in some terrestrial deposits they'll get buried. The Copper Harbor conglomerate up in the UP, those ripple marks, you get a subsiding basin. As that basin subsides, you'll get ripple marks form. The basin subsides, the more deposits come in, forming more ripple marks, bringing in more sediments, maybe some pebbles, maybe not, depending on how fast the water's moving, bringing it in, or how high the tide is, or if there's a storm or not. The Baraboo seems to be mostly deposited pretty quiet waters. So as that basin subsides more, you get other beds deposited on them, and it happens more, and other beds deposit upon them. This is part of the tectonic process, basin formation, basin deposits. Depending on where your source area is, you're going to get different rock types. If you have carbonate deposition, you're probably not going to have a lot of clastic deposition. You'll get mud. If you don't have a lot of mud, you're going to get sand and stuff like that. It all depends on where you're deriving your sediments from, or what's going on chemically with the water that's interacting with it. All right? It has nothing to do really with whatever you're talking about. I don't even know. All right? So let's just move on.
That's the take home. You want to talk about that. You want to know something about history. There was a man who in the 1940s was at St. Anthony Falls Lab, and he was watching the flume form sandy layers through a wall of glass. And he convinced himself that sand was deposited rapidly.
Okay, I'll just take his story at face value. I have no clue what he's talking about, and I only have a vague picture of what he's trying to speak about. So, let's see. Just because you can deposit something rapidly doesn't mean you did, right? I mean, I just showed you, how I take you places. I've described places here. Sediment transportation is very important. When we talk about sediment transportation, let me get out a map for you so I can demonstrate this. When we talk about sand being transported over long distances, we are talking about a net distance. We are not talking about, say, just using this as say that the sand that forms this started here. If I have a well-rounded piece of sand, but it's only right here, that doesn't mean it only went from here to here. That's not my net. What probably happened was it got eroded, formed something bigger, came down, my seas bashed it against some cliffs, brought it down, more cliffs, brought it down. See, you can do this here. You get your pebbles were broken off. This is your cross section now. Seas bash it back in, bring it out, bash it back in. It could travel dozens or hundreds of kilometers before it ever gets buried and preserved. That is more than enough force to round rock. You can't round pieces of sand like this on this volume from one event. It just wouldn't happen. And like I told you, the Galesville, that's pretty round. The St. Peter, the Ordovician Younger St. Peter, which we aren't visiting here, but it is in the area, has matter of fact, it's one of the best sandstones in the world. Everyone goes to it to study. You can't get that in a catastrophic environment. It takes time. I can take that sand and dump it out and make a big hill out of it really quickly, but that doesn't mean that's what happened. You have to look at the rocks. You have to study the type of environments that these things are produced in. On my scale, and it depends on what your definition of quickly is. Is your definition of quickly a minute, an hour, a week? I mean, we're talking about the Precambrian. We're talking a couple million years minimum, even not dozens of millions of years, and even in the early Phanerozoic, we're still talking large amounts of time. From a geologic standpoint, that seems quickly, but none of this happened in a year. You can't fit this into a year, no matter how hard you try.
He saw it form at, millimeters per second, that kind of thing.
Who cares? If I don't have the sand to deposit in millimeters per second, I'm not going to get sand deposition in millimeters per second. Beds contradict exactly what you're saying. We would see massive sand. We wouldn't see bedding and cross beds and all this other stuff, Steve, and you know that. At least you better.
They can engineer the process that makes it.
What's your point, Steve? That's called a model. It doesn't mean an engineer, it doesn't mean a builder did it. You're trying to model something. You're trying to reproduce what you observed. We don't observe that. It's not a reproduction of nature. Not here. You can't extrapolate something, one experiment, to every place on the planet, or one demonstration, whatever. We don't see that. I don't see any relatively level beds. I don't see this type of sorting in your model you just showed. So what that means is some other process happened. Something else did this.
And the ripple beds can be formed rapidly, but we're looking at something really interesting here. When we see the cobble layers with the sand in between, but if that was deposited slowly, what would happen? The large rocks would settle and the fine sand.
That's under the false assumption that the water carrying the sediment was at a consistent velocity. He just talked about varying fluid velocity, although he didn't use the correct terms. But if your ocean doesn't have sand to go up and down that beach, you're not going to have a sandy beach. This has to do with more than just stuff settling out of water.
Would float, and the cobbles
suspended in solution, suspended in your water. We don't use the term float. He's talking as if sediment floats on top of the water. That's the picture I'm getting when he's using that word. It's suspended in load. Okay, it's a load and suspension. Sorry, but we're getting near the end. Home stretch.
I have talked about the Bible ad nauseum.
I love it.
Yes,
but you don't accept it.
No, it's not that I don't accept it.
Oh, okay.
It's that.
And that's fine. He doesn't have to, he can accept the Bible and just not take it literally. There's nothing wrong with that.
I take the physical processes that I can witness and that I can study, and that is what I decide to.
So when you talk about reality, if you can't measure it, if you can't do experiments or make demonstrations, make models that make predictions that can later falsify or strengthen your hypothesis. If you can't do these things, your interpretation is meaningless. Yes, theories are interpretations. That's what they do. They explain our hypotheses and maybe other theories and other process, but it's a well-vetted thing, and theories don't come about based off lack of evidence. It takes a while to develop these, and some are so well developed we work within them. We're not always trying to make new theories. That's not how we work. Okay, so you can't just take measurable reality and interpret it any way you want. That's not realistic. A global flood over a period of a year violates so much of what we know. I mean, granted, we don't know everything, but we know a lot. And I'm using that word because in science we never prove anything. There's no inherent truth. So I'm using the term more loosely. But we do know some things. Okay, knowledge has been gained, and everything we've done since then has supported that knowledge. So that's essentially a fact. All right, you can't just take everything and just rearrange it to fit something while ignoring everything else.
To move.
By the way, these tracks are active. Some of the trail does cross them, but just so you know, this is along the East Bluff, I believe. These tracks are on the East Bluff. I see people walking up and down them. Safety minute here. These tracks are active, and if you're on ground level, you will not hear that train until he comes around that curve. All right, if you're up on the bluffs, you hear. But if you want to cross it, yeah, the trail goes across it. They're not going to stop you. But don't walk along these, okay? There's nothing that interesting here. And it's not a shortcut either. It really isn't. The path is just as fine.
All right, so we're going to take Potholes Trail up to Devil's Doorway.
Okay, so now he's on the southeast part of Devil's Lake. I might have to get my map back open again. So it's somewhere over here. The tracks. This is a very difficult way to go up. It's very hard. I don't know how they came, but it seems that him crossing the tracks, maybe they went up, came back down. Was like, no, you go up this way. Just keep going. Just keep going. You know, because you have to go up this way. It's hard. Let's see here. This is it. That's this. And here's the moraine. You can see the moraine right here. Johnstown Moraine. That's this. Nothing else I want to say about glaciers, too. When we talk about ice ages and glaciers, we're usually talking about Quaternary, the recent modern glacial periods. Us Precambrian guys will call it modern, even though that goes back 2 million years and there's different, episodes and stuff like that. But that is not the first time. Now is not the first time we've had ice ages. Some people are aware of like the Ordovician ones and stuff like that, but it's not even it either. And that wasn't even an ice age Ordovician. We just had a south polar cap. People define ice age a little differently. This is one of my roadside books from Ontario. Am I recording? Okay. Let's go. I am going to show you the ultimate glacial deposits within the Precambrian, the oldest confirmed ones. You don't have to go to really exotic places to see them, although there are in places in Africa as well, and I believe Australia. Yeah, Australia has a few, I think. But they're best preserved here. And this is the Huronian supergroup. We have several glacial this is the initial. The Huronian supergroup is interpreted as a passive margin sequence. You had a rift valley form and eventually moved apart like the Atlantic Ocean, like North America did from Europe. So you get volcanics at the base, you get sediments, but this, glacial. This is glacial. None of these others are glacial. The glacial deposits, this old. Wait, did I have years on there? Yeah. You can generally get a general idea. This is in millions of years. So this isn't last week. This is Paleoproterozoic. 2,318 million years. We're talking a long time ago. And they ended about 2310. We'll just round it down, even though they ended before that. So 2,320 million years ago, or 2.32 billion years ago, is about when they ended, a little after that. Here, I'm going to take you and show you the Gauganda. This is it. This is that top one. Basal cobalt group. And these are thick in places. Some comparable, and it's several cycles. And you can see here, this is a diamictite. This is till that has been metamorphosed a little bit. And you can see dropstones, cobbles, you have sandier units, you have more shaly units. Modern Quaternary deposits aren't the only glacial deposits in the rock record. We have them in the Precambrian. You can't explain those through a flood. I mean, you just can't. The glacial deposits here tend to be sandier. All right, there are some places that look identical. The modern ones are just really hard because they've been slightly metamorphosed. But we see the best preserved ones because these glacial deposits were near shore. So they get preserved better. Marine deposits preserve better than terrestrial ones. Doesn't mean we don't get them. It's just the general rule, the way the rock record is, because usually you have a basin type environment, so you have more subsidence, so they tend to get preserved better. And so why aren't any of these in the Parfreeze Glen. We have granitoids, we have jasper, we even have the occasional arcosic sandstone. All of this stuff is from relatively nearby. The preserved glacial deposits in the Precambrian are more locally sourced. You do occasionally see the odd stone, which is further support that this is glacial. In other locations, it's not well bedded. At other locations, it looks like a typical till. You'll see the occasional boulder, pebble, cobble in a clay-type, silty-type matrix.